Right, I believe we're going to make a start just to comply with the agenda. So we were meant to have some reflections on day one of workshop, but just briefly, I believe we have a fantastic day one yesterday with beautiful presentations from colleagues all over the world. Also a nice lunch by the river. Today we have the same restaurant, that's a good thing. So we have a beautiful agenda ahead of us with talks from different companies and academic colleagues. And it is my pleasure to introduce the opening lecture today, which is coming from CEPSA. We have Joanna Frontella, who is research director at CEPSA, with a very appealing topic, circular economy and decarbonization at CEPSA. So, Joanna, many thanks for taking some time of your very busy agenda to be with us today. And whenever you want, the floor is yours.
Okay, thank you, Thomas. Thank you for the introduction. Good morning, everyone. It's my pleasure being here with all of you in this interesting workshop. I'm sorry I couldn't attend yesterday, I would like, but my agenda, as you mentioned, is horrible. Well, the topic of the conference is very ambitious because I will tell you about the ambitions of CEPSA about circular economy and decarbonization. First of all, I would like to introduce a few words about the company I represent here. CEPSA is I would say it was a former oil and gas company. We started the operation a century ago, so in the 20s, last century. And at the beginning, we were just oil and gas company, mainly oil, mainly refining. And in the latest 80s, we started with petrochemical. So at the end of the last century, we were a refining and petrochemical company. That's it. Today, in the 20s of the 21st century, we would like to be an energy company, not only oil and gas, but also including in our portfolio the production of sustainable energy. And to go to the green ball, to going beyond net zero emission, which is really, really ambitious. If we look at what is happening in the world today, we can see here that the companies or the industries that produce higher emissions in terms of CO2 are the industry and the transport sectors. My company is in both places, so the production, we produce energy, but we consume a lot of energy, and we produce fuels for transportation. It seems clear that the crude will end up as a chemical producer, because today more and more problems are coming due to the emissions related to the fuel base in petrol, in crude oil. As any oil company, we have to fulfill the specification of the fuels in order to sell them. The legislation in Europe is very strict, and we have to comply with every property of the fuel. It was our biggest challenge till last year, but in 2021 we received a new package of measures regarding, in this case, the emission we produce or we are responsible for, because our production scheme produces the emission of a lot of CO2. We contribute to the emissions in three scopes, scope 1, 2, and 3. And in 2021, it was a package in order to reduce the global emission in Europe. This package is not approved, but it will be very, very soon, we guessed. Where are we in the emissions? I mentioned there are three scopes. Scope 1, can you see? Yes. Scope 1 is the emissions we produce in our operation in the refinery. the furnaces, the steam reformer. There are a lot of units in the refinery that produce a lot of CO2. All of them are the scope 1. The second scope, the scope 2, is the emission of the energy we use in the refinery, the energy we use for the production of this energy or this product, for example, hydrogen. A lot of CO2 is produced, so this contribution is scope 2. And scope 3 is the total emission produced by the combustion engine of the vehicles, for example, the car, the train, the ship, etc. What are we doing? Where are we working in to reduce the global emission? We are working in scope 1 with energy efficiency projects in the refinery, how to reduce the energy input in the refineries with the development of new processes and new catalysts, for example. And in the scope 2, the ambition of the company is to be autosufficient. That means that we would like to produce our own energy by renewable energy, wind, solar, etc. And scope 3, the only way to reduce the emission of the fuels in the engine, in the cars, is if we produce biofuels. That means that in the petrol or in the gasoline, kerosene, or bunker for ships, the higher the quantity of bio component we blend, the lower the emission we produce. So we are working in the 3 scopes because our ambition, our target is by 2030 to reduce or to increase the renewable content of our energy by 32%. This is what we would like to be in the future. It's a dream today, but we would like to be like this. We would like to have an energy park. We don't call refineries as it was in the past, because now we want to be a global energy parks in our refineries. So we would like to install renewable sources in the refinery to feed the normal units, the refinery itself, with crude oil, renewable energy, and bio streams coming from biomass and from waste recycling. I will talk later about this. For producing biochemicals, fuels for transportation, and other products. So this is what we would like to be in the future. For sure, it's a great challenge we will have to cope with. In this sense, I would say that the research work is crucial. For me, I am a researcher. I started probably as many of you in the academic, in the Spanish Council, and my message is that we have to give our best, to do our best for solving these challenges for the future of all of us, the society, I mean. About the chemicals, CEPSA is best in class in 2 products, linear alkyl benzene for detergents and phenol. And our goal or our aim is to produce them by using biomass, so for producing biodetergents and for producing biophenol. The phenol is the raw material for producing a lot of polymers based on phenol. So we like to be more sustainable in the petrochemical products. As I mentioned before, it must be done with a lot of research. It's clear that we have a great challenge to cope with, but we would like to well, let's say that the society is putting a lot of pressure on us, so we have to do our best to go further in this topic. Let me go directly to this slide. In Europe, in the Europe of the 27+3, we produce near 30 million tons of plastic here in Europe. Half of it are mixed, is a blend of different plastic, And the other 50% is you can sort and classify the plastics. This part, let's say the one that can be separated, is much easier to recycle because you have the polypropylene, the polyethylene, the polyvinyl chloride, everything is separated, so you can enter it in the recycling process easily. But the 50% that can be separated, so the 15 tons, million tons per year we produce, is a blend, is a horrible blend, where everything is mixed. So you have a blend of polypropylene, polyethylene, polyvinyl chloride, polyestyrene, polyethylene terephthalate, everything is mixed. And this is very difficult to reuse. To give more pressure on this situation, let me go to no, I can find, where is it? Well, I can't give you the details. Last year, we received an announcement that there will be a fee for the plastic that are sent to landfill, because the normal end of the mixed plastic that we're not able to reuse is to send to landfill, to vertedero, we say in Spanish, to landfill. But now this is forbidden, so we have to do something with the mixed plastic. Again, this is a challenge for the researchers, so we have to do something with the mixed plastic. The mixed plastic is a blend. Here you can see on the right what is the, let's say, average composition of the plastic. On the left, you can see what we throw to in the rubbish bin, and only 7%, so less than 10%, is a plastic. The main composition is plastic. And this 7% is, well, 33% is polyethylene, low and high density, 25% is polypropylene, and 20% is polyvinyl chloride. The rest is a blend. When we have this horrible blend and we can sort it, we have everything together, and we need a robust process to recycle this, to convert this into something. What do we want to go with the mixed plastic? We would like to produce fuels based on waste and also petrochemical. So you can imagine that the idea is to take them, to convert into something to put in the refineries. This is what is the business case, because it doesn't make sense to build up a refining place for processing just plastic. So our idea, our and other oil and gas company, is to introduce the plastic streams in the refineries to work together with the crude oil, with the normal crude oil. I recommend you to have a look on this diagram. For me, it's very interesting. Probably it's difficult to read it, but this diagram is taken from the circular economy for plastic from Plastic Europe. It's very interesting to have a look because you can see the different places in the value chain of the plastic where you can do something to try to make more sustainable the global business of the plastic. In the black label, you can read the improvement considering the 2018 compared with last year. And you can see here that in any of the steps of the value chain, there has been an improvement. So today, we are seeing a better or more sustainable use and process of the plastics. It's very interesting. I recommend you to have a look on that. As I mentioned, what do we want to see? We want to work in this part. We are not in this part because this is other value chain where you have the consumers, the classifying, the sorting. We would like to convert chemically the plastic to produce a kind of pyrolysis oil. And after a polishing, we can produce fuels or chemicals. This is a normal pyrolysis oil. Later you have we have a conference of one company that has this kind of technology for producing this product, and when we submit this or send this product to a crude oil distillation column, we observe something similar to crude oil. So we obtain from gasoline to a very heavy product that can be used for asphalt production. So we have a kind of, let's say, crude oil based on plastic, but it's not as such. It has a lot of contaminant, and I mentioned here the polishing steps, because as it is produced, this product is difficult to process in the refinery, because the refinery is prepared for processing crude oil, not plastic. And the plastic contains a lot of impurities that are poison for the commercial units. When we look at the plastic, even if we have this bottle, which is polypropylene, 100%, there are some impropers in the composition of the plastic. Here you can read that, for example, polyethylene terephthalate, if you have a residue mainly of polyethylene terephthalate, only 95% of the solid is plastic, is the polymer, but you have 4.5 of impropers. Impropers can be sound, can be fevers, can be water, can be a lot of things. So if we process any of them, we will have to cope with these impropers, which are in some cases very, very high as 20%. So imagine if we process everything together, we will have something like this, but a lot of residues that are difficult to work with them. Where are we working in research? In order to have a product able to process in the refinery, we are working with 3 different lines. One is the gasification of the plastic. The plastic can be decomposed to produce synthesis gas that will go further with Fischer-Tropsch for producing methanol or paraffins. Here I give you some details about it, about the process, but I would say that the syngas produced is a mixture of carbon monoxide, carbon dioxide, hydrogen, water, and a lot of impurities. I mentioned before the impropers that contain the plastic. So it will need a very, very precise polishing steps in order to purify the syngas, because the catalyst, the Fischer-Tropsch catalyst, is very sensitive to poison. So here is a normal scheme of a process going from plastic to methanol, for example, and the plastic conversion is this first step. The other ones are due to polishing steps, so it's bigger, the polishing area, than the conversion of plastic. So this is a challenge. The purification of the syngas produced by gasification of plastic residues. Other process we are working in and we are evaluating technologies. We are not technology developers. CEPSA, we are not technology developers. But we are working together or in collaboration with technology companies in order to, let's say, improve for example, the pyrolysis process for producing cleaner streams to introduce them in the refinery. So the pyrolysis is a thermal process that can use or not catalyst, so you can get a kind of selectivity if we use the catalyst, but our experience in the laboratory is that the catalyst is heavily poisoned in very short time. So we need a process where the catalyst can be regenerated, so kind of FCC process, so the catalyst is going through between the regenerator and the riser continuously in order to regenerate the catalyst. But the catalytic pyrolysis is still, for me, in a development step. I mentioned before the pyrolysis oil. This is, for example, the composition of one of them. There are a big variability of pyrolysis oil depending on the raw material you feed the pyrolysator. So here you can see that it can contain a big amount of mercury, arsenium, silicon, iron, other metals. So it's a nightmare. We have to introduce this in the refinery because the impact in the commercial unit will be huge. So it's unaffordable to use it in the refinery. This figure, I took it in 1 year or 1 year and something ago. They represent the efficiency of the process from different technology suppliers and the modularity. Why? Because the plastic as raw material is not as crude oil. We have big ships in front of the refinery with 1,000 tons, million tons of crude oil feeding the refinery. But in the case of the plastic are spread everywhere. So we have other problems to take into account. That we can't move plastic from, I don't know, from Zamora to Algeciras refinery. It doesn't make sense. So it seems better approach to have a small unit, modular unit that you put close to the residue collector in order to get to transport just the py oil, not the plastic. So this is very important when you have to study or you have to evaluate your business case, the modularity of the technology. Other process we are looking at it, the hydrothermal liquefaction. For me, this is a very promising technology. It's a kind of pyrolysis, but it's produced at high temperature and under water pressure. High temperature, high pressure, the quality of the product is much better than the normal pyrolysis. The impurities of the containing in the plastic are normally in the liquid phase, so you have a separation. The quality of the pyrolysis oil is not as bad as the normal pyrolysis oil. So it's more promising, this technology, but it's under development. I don't know, but up to my knowledge, there are no commercial units running 100%. There are demo units, companies building up the first commercial unit, but there is no one running up to my knowledge. So, but this looks very promising. In terms of economics, this process is higher in capex than the pyrolysis and the gasification. Just in order to compare the three technologies we are evaluating at pilot plant, and we are evaluating the quality of the different oil, working with different technology suppliers, we can say that the comparison between gasification, pyrolysis, and hydrothermal liquefaction is that the higher yield is obtained with hydrothermal liquefaction, and the quality of the product is much better. My concluding remarks is considering the amount of plastic we have in the world we use, and it seems that we will go further in the plastic consumption because the figures show that we will need more and more and more plastics. The recycling is a must. We need to recycle the plastic, we need it. For sure, new business will be developed around the plastic circularity and the business of plastic. We need them. The technology we have today are not perfect. We are still in in the improvement of this technology, and it's an open room for all the researchers. For sure, research activities are crucial. I am a strong supporter of that. I strongly believe that is a great opportunity for all of us to try to improve the technology for the use of plastic and biomass. I didn't talk about biomass. It's other word, quite similar to plastic with differences, but is new in the refineries, and we have the spread, the raw material availability, the stationarity. We have other problems, but we have to work with both plastic and biomass. The catalyst, the catalyst is a word to discover. We need better catalysts with better selectivity, stability, and so we need a big effort on research on that. And we also need the legislation to come with us, because today it's difficult to enter or to fit with this kind of oil into the refinery. We need a special permission to do that. It's needed a kind of certificate to show that we are not using residues for producing fuels and chemical, for sure. So this is my final conclusion, and that's all. Thank you so much.
Joanna, thank you very much. Well, that was a beautiful, inspiring talk, and you put the ball on our ground for the academics to do some research. And I could see some smiling faces on the PhD students working on plastics and biomass, because you are inspiring this young generation of researchers working on that. So thank you for that. And we have actually time for a couple of questions and open the ground for discussions. She was a bit faster. Okay. So, Julia.
Hello, Juana. Thank you very much for the presentation. My name is Julia. I work for Green Delta in Germany. And my question is related a bit to the first part of the presentation. It's very interesting to see how CEPSA is evolving. And so, more than with plastics, recycling, etc., I wanted to ask you how CEPSA sees hydrogen as a potential fuel for the future to move to a more sustainable world, and if it's investing in any hydrogen technologies at all. Thank you.
Thank you for your question. Well, CEPSA has announced this week that we have signed an agreement with the Rotterdam port in order to supply with hydrogen in form of ammonia and methanol. So, and on the other hand, we are installing 2 electrolyzers in the south refineries, in Cádiz refinery and in Huelva. So, we think the hydrogen is a promising energy vector. We are not doing anything in research about it, to be honest. In the research center, we don't have projects for improving the membranes or the electrodes. No, we don't have it. But the company has announced the production of hydrogen 2 giga by 2030, I think. So it's huge, the amount of hydrogen we want to produce for the future, because we strongly believe, together with the ships companies, that the hydrogen can be a very interesting and important vector for maritime transport. Yeah. Thank you.
Hello, Juana. Good presentation. Thank you. I'm from Chile, from the Pontificia Universidad Católica. I just wonder what happened with the CO2 when you burn the fuel obtained for plastics, because that is not sustainable. But I don't know, CEPSA has some plans to recycle the CO2 or for absorption of the CO2.
This is one of the for me the key question. If we have to go to net zero emissions, it's clear that all the processes that need energy for the production have to change. We have not only to let's say, produce biofuels 100% bio, because we need energy for production, and this energy emits CO2. So the approach is that we will need to use the CO2 emitted during the production process, and this is connected with the research project ongoing in all the European Union for utilizing the CO2 for producing methanol, other chemical, formic acid, and so. Because if not, the emission won't be zero, and we will need it. So we'll have to do something. This something, even at lower TRL, the production of something coming from CO2. We have a huge challenge for the scientific community, it's clear. Yeah, thank you.
Last question over here. Hi, Jacopo Tattini from Joint Research Center. Thank you very much for the presentation. I found very fascinating the concept at the beginning of your presentation of the energy parks. And I was wondering if you can tell us a bit more about this vision. Would you see, for instance, the production of hydrogen, ammonia, and biofuels happening in the current oil refineries when the oil consumption decreases? And how to square this with the fact that you mentioned that biofuels and also biomass is available in more widespread way, and also, you know, hydrogen costs a lot to be transmitted, much more than fossil fuel. So would you have more of these energy parks around Europe than how many refineries you have now? Thanks.
Thank you for the question. Now we are entering in a business that is completely different than the crude oil. CEPSA and probably all the oil and gas company, we cover all the crude oil value chain from well to wheel. So from the well where we produce the crude oil to the car vehicles. But the circular approach or the sustainability approach or the energy park approach, as I showed you before, require not only our contribution, but we strongly believe that we need the collaboration of other players in the business. For example, companies that produce ammonia. We don't produce ammonia. We don't. But if we have the hydrogen and we create alliances or strategic alliances or collaboration, or we are signing, I don't know, a lot of memorandum of understanding with companies, because we need to play with others, because many things we want to be are out of our expertise. So we need the collaboration of others, companies for producing ammonia, or companies that take the plastic for producing the bio-oil, because we know what to do with the bio-oil, but we don't produce bio-oil. So the business will be bigger. With other players, we will probably found a community of companies for this approach. And as we do, probably most of the oil companies will do the same, because many things are out of our business today. Thank you.
Thank you, Joanna. Thank you very much, and we thank the speaker again.
Thank you.
And also thank you for sticking to the timing. This is perfect timing. Thank you very much. So the next speaker is coming from LICAT. It's Professor Angelica Wigner. She's one of our partners in BIOALL project. So Angelica, thank you for coming along today. And you can load your presentation and we make a start.
One moment. Okay. How can I get it to the...
I guess you have to just execute the part
okay, yeah.
mode, right?
Okay,
And it
perfect.
should be running well.
Yes.
Right, the floor is yours.
Yes, so, thank you very much. Good morning, everybody. Today I would like to present to you some activities of sustainable catalysis in our institute, but I will mainly focus on the CO2 conversion. So let me start with a few words of the institute itself. We are located here in the very northeast of Germany at the Baltic coast, and this is our main building here. And we are very proud that we could open our new technical facility, which is here, in July this year. And we are well located here because all these buildings you are seeing here, they belong to the University of Rostock, to the Natural Science campus. And so due to this close neighborhood, we... Okay, yeah. Due to this close neighborhood, it's easy to establish joint and run joint collaborations. So the institute is already quite old. We have our 70th birthday this year. It was founded in 1952 in Rostock as an institute of homogeneous catalysis. Then it was separated in two parts shortly later. And 2006, back to the roots again, the two parts were rejoined in Rostock, and then this was the time where we got these new buildings. And as I mentioned already, now we have also a technical facility. We are around 300 co-workers, 100 of them are PhD students. Our basic funding is between 13 and 14 million per year. And this is coming from the federal government and from the government of Mecklenburg-Vorpommern, where we are located. And then we have about 8 million euro external funding, which is coming from industry, but also from public projects, among them, of course, also the EU. We have between 300 and 350 publications every year, 40 patents in 2021. And now LICAT is one of the largest publicly funded research institutes in the field of applied chemistry in Europe. Our mission is to transfer basic knowledge to application. So in industry, they realize, of course, processes and they have their own very application-oriented research. And then we are in Germany very strong in basic research. So we have the Max Planck Society, you all know this. And then besides this, we have Leibniz and Fraunhofer societies. And the Leibniz and the Fraunhofer, they are focusing the research on the bridge between basic and basic research and realization. And this is also our approach, to always perform not purely basic research projects, but projects with a certain aspect of application. Accordingly, we have lots of collaborations with industry. These are our main partners here. And these three are, so to speak, our gold sponsors. We are running laboratories together with them in our institute. This is the structure of our institute. This is a little bit busy here, this picture. We have 10 research departments with 29 research groups here, and also 2 junior research groups. And we have close collaboration to professors at Rostock University and also at 2 other universities in Germany. As you see here, we cover all fields of, almost all fields of catalysis, from applied homogeneous catalysis, heterogeneous, reaction engineering, photocatalysis. This is also homogeneous catalysis with ligands. Quite new departments are these ones, catalysis with bioresources. This has been established only 2 years ago. And there is now a topic group which combines both aspects. They want to explore the synergy between homogeneous and heterogeneous processes. And then we have a new department of electrochemistry since last year, and in collaboration with university, also biocatalysis and polymer chemistry. And the speciality of the research in the institute is that we have defined task-oriented collaboration within 7 topic fields. So the topic fields are related to the research needs which are most important nowadays. So in these 7 topic fields, the research departments and the research groups of the institutes work together. So, and this structure is quite flexible. Depending on the projects and the collaborations, research groups can enter and go out. So we just have the research field established, but the participants, they change depending on the projects and depending on the need of the current research. And now I want to go through the activities of some of these topic fields which are related to CO2 conversion. So the topic field 1, structure-reactivity relationships, this is ours. We are focusing on the development of modern characterization methods and setups by which we can monitor catalytic processes and catalysts under reaction conditions. And the ultimate goal is to make catalyst development more efficient based on a rational knowledge and not just based on trial and error procedures, which are still dominating in catalysis. So the main objectives of our department are development of simultaneous couplings of different spectroscopic techniques to make this research more efficient and the results more reliable, because we apply these methods in the same system at the same time, and so we can prevent errors that arise when you compare results obtained from different methods in different setups. We want to adapt these methods more to industrial reaction conditions. That means we want to develop such methods for higher pressure, enable the possibility of electrical potential. We want to work we develop flow reactors for this, and also conditions to use polar solvents, which is not always easy in spectroscopy. Also, increasing the spatial resolution is an issue. And for that, we have brand new machines for near ambient pressure XPS and also for near ambient pressure transmission electron microscopy. I come to this later. And another issue is automatic data acquisition, evaluation, and mining. And we have in Germany since last year a big network of national data infrastructure for catalysis, where such tools of data mining and evaluation are developed, and we are part of this. This is, for example, the very first 5-in-1 coupling technique. Jabor is here the leading person for this, and we have also a patent on it, which we in the meantime sold to Bruker. This is our new high-resolution transmission electron microscope, which we acquired together with university in a network of electron microscopy center in Mecklenburg-Vorpommern. And the speciality of this machine is that we have such micro electromechanical holders, such MEMS holders, in which the sample is located between windows of silicon nitride, and with this holder, the sample can be analyzed at ambient pressure and up to temperatures of 1000 degrees C and under flowing gases. You know, usually electron microscopy is a vacuum method, but with these holders we can really do these measurements in operando mode. The topic field 2, kinetics, theory and mechanisms, is closely related to our topic field 1, structure-reactivity relationships, because they want to elucidate reaction mechanisms on the elementary in elementary steps on the elementary level. And for this, they need knowledge about active sites, species, and phases. And this is coming from our topic field here. And they focus on the determination of kinetics and product formation. And all these results are used for developing fundamentals for purposeful catalyst design and preparation. And their activities in CO2 conversion are focused on 4 aspects. This is dry reforming of CO2 and methane to syngas, CO2 and olefins together with hydrogen to alcohols, and the CO2 Fischer-Tropsch to hydrocarbon, and the hydrogenation to methanol. This project here, this is a joint project between the 2 topic fields, hydrogenation of CO2 to fuels, so Fischer-Tropsch CO2, and we are doing this with iron-based catalysts under dynamic operation conditions. The idea behind is when we produce hydrogen by using wind and solar power and so on, this is provided not continuously, but it fluctuates. And when we want to avoid the intermediate storing of hydrogen, we need processes that tolerate that such fluctuating hydrogen. And this is the idea behind dynamic operation conditions. So in our department, we have developed high pressure IR transmission cell to follow this process. You see this here. This can work at pressures up to 30 bar and temperatures up to 300 degrees C. It's easy to assemble, and it's connected to a gas supply and also to a mass spectrometer for product analysis. So this is really a miniaturized IR reactor, which is used for exploring structural reactivity relationships in this project. And here you see some results. The spectra have been recorded at these reaction conditions. We see, and we explored here the dependence on pressure. And we see that at 1 bar, at normal pressure, we have almost no conversion. So we have to increase the pressure to get conversion of CO2. And when we increase this pressure here, you see that we observe the band of gaseous methane and the bands of adsorbed CH3 and CH2 groups here. And with increasing, and of course we see also gaseous CO. This is one of the products as well. And with increasing pressure, we see that these bands are gaining intensity, and also the ratio between the CH3 and the CH2 band here, the red and the blue one, the CH2 is increasing. This means we detect here a chain growth to higher hydrocarbons. And this, of course, is depending on the pressure. We use iron oxide-based catalysts for this reaction. Usually we are starting from such bulk iron oxides, and under reaction conditions, these iron oxides are reduced to magnetite, to FAO, to iron, and finally such carbide phases are formed. And these are the active ones in this project, in this process, which happens under reaction conditions. And what I show you here This is analysis of such iron oxide precursor in this MEMS reactor in this new high-resolution TEM machine. And when you look here, you can see that the iron oxide is transforming at 400 degrees C in CO2 hydrogen-helium flow to such iron carbide phases. And we have found that the reduced magnetite is responsible for activation of CO2 to CO. The iron, the metallic iron, should be avoided because it's forming mainly methane, and this is not the target product in this process. And finally, these iron carbides, they form, they are responsible for the formation of higher hydrocarbons. And this is the catalytic test. This just shows what I just mentioned. We have here different catalysts, differently prepared. In these catalysts, we have a different amount of the carbides and a different amount of iron, which is formed under reaction conditions. And you see clearly with increasing percentage of the carbide here, we have an increasing selectivity of the higher hydrocarbons. And with increasing percentage of the metallic iron, which should be avoided, the selectivity of methane increases, which is detrimental in this process here. The topic field 3, reaction engineering and implementation. The main aim here is to transfer results from laboratory to technical scale, and they are the main players in our new technical facility. And they want to develop the best possible reactor and operating regime. And another issue is enlargement of catalyst preparation from the gram to the multi-kilogram scale to approach industrial conditions. And also they are very active in this national data consortium. This is an example of hydrogenation of CO2 to methanol. And they used here a membrane reactor for this reaction. And with the membrane reactor, they removed the water from the process. So it is possible here, by removing this water, to shift the equilibrium more to the methanol side. And this is a comparison of data from literature. This is the equilibrium line for the yield of methanol here, and you see that they were able here to really increase the yield of methanol and shift the equilibrium more to the methanol side by using this membrane reactor. This is another example here. The aim was here to hydrogenate CO2 to methane, and usually in this reaction, at low temperature, there are deactivation processes. At low temperature, the methane can decompose and form carbon, and at higher temperature, you have the boudoir reaction, which forms also carbon. And by doping a high surface area support, this alumina here, with different other metal ions, it was possible to increase the stability of the supported nickel particles, because the nickels are the hydrogenation, is a hydrogenation catalyst. And you see here, when they introduce lanthanum and such a chelating agent, citric acid, they were able to increase the metal support interaction and to keep the nickel particles dispersed by a stronger metal support interaction effect, and so they could suppress here the fast deactivation by sintering and also by carbon formation. Topic field 5, energy and environment. They are focusing on using sustainable resources for circular energy. And the main fields where they are active is hydrogen production from renewables, the use of hydrogen for liquid fuels, and to explore the potential of photocatalytic and electrochemical processes for the production of valuable chemicals. And they also try to reintegrate gases such as CO2 and methane, greenhouse gases, into the chemical production. And the examples I want to show you here, they are from the photocatalysis group. They want to try to convert CO2 photocatalytically to hydrogenate this. And for this, they have developed a high purity reactor here. So you probably know from literature that there is a huge amount of papers on the use of titania to hydrogenate or to convert CO2 with reducing agents such as water or organics to mainly such as water to hydrocarbons or products from CO2. The problem here is to really ensure that the products are coming from the CO2 and not from organic impurities, which are still from the synthesis in the titania. And they have realized this problem, and for this they have developed this reactor which is free of any grease. And apart from designing this advanced reactor, they focus very much on blank experiments to really ensure that the products are coming from the CO2, and for this they also usually introduce cleaning steps before they start the reaction. And one example is this one here. They use CO2 and isopropanol to hydrogenate CO2, isopropanol instead of water. And what you can see here from these curves is that in the presence of CO2 and isopropanol, less products are formed. These are these curves with the open symbols. Then when they use the isopropanol alone without CO2. And this clearly shows that from that catalyst, no products from CO2 reduction were formed. And all the products they detected, they stem from photocatalytic degradation of the isopropanol. And this again illustrates the necessity of careful performance of such photocatalytic reactions and to be aware of all the problems here. This is an example of simultaneous capture and utilization of CO2 by homogeneous catalysts. This group used, inspired by nature, amines to absorb the CO2. On this overhead, I just show you the absorption process. On the next one, we have then the simultaneous catalysis. So, and from the many amines, they tested the lysine was the one which was most effective for absorption of CO2, probably because this molecule has here such a basic side chain. And they tested this for different pressures. So here you see that at 20 bars of CO2, they were able already after half an hour to obtain a yield of 98%. Interesting is when they performed this reaction at lower pressure here at 2 bar, in the very beginning, after half an hour, mainly these carbamate products are formed upon uptake of CO2, and only later these carbamates are transformed into the bicarbonate here. And they also used this system for removal of CO2 from ambient air, which has only a content of CO2 of 450 ppm. And even in that case, they were able to reach 98% yield of CO2 adsorption within these products within 1 to 8 days. And this is the result of simultaneous catalysis. So they use such ruthenium complexes, and these two here were the best ones, producing a yield around 40 to 50% here. And this worked also when they used this CO2 which was absorbed from air. The topic field 6, more efficient processes, they also focus on the development of microreactor and membrane technology to make processes continuous and reduce the use of resources. And this is groups from homogeneous and heterogeneous catalysis work together. They try also to make the ligand design for homogeneous catalysis more efficient and develop novel heterogeneous catalysts by avoiding noble metals. They should be non-toxic, and they want to prepare them from renewable resources. And the aim is to develop new preparation and simulation tools to increase the technical readiness level for such reactions to be performed in our new technical facility. And this is one example from them, from the CO2 to syngas conversion. In this reaction, there are two competing reactions. This is the reverse water gas shift and the Sabatier reaction here. And both reactions are catalyzed by nickel, you know this. And these are data from literature showing the dependence of the product selectivity on the nickel particle size. You see that with increasing nickel particle size, the CO selectivity is increasing and the methane selectivity is decreasing. And now this group developed new core shell catalyst here with a copper core inside and a nickel oxide shell around. And with this, surprisingly, the selectivity to methane was 0. So they could completely suppress the Sabatier reaction and only perform the reverse water gas shift reaction with 100% selectivity to CO. And this even worked when the CO to hydrogen ratio was 1 to 4, which is usually characteristic for the methane formation. And another example from this topic field is CO2 hydrogenation to medium chain alkanes. And this is an example where they tried to develop a novel reactor concept, a bubble column reactor, to make this process continuous and to produce and separate simultaneously gaseous products and liquid products. And the catalyst is mixed oxide containing these components, and requirements here are that these catalysts must be sufficiently abrasion resistant and a fluid dynamic density of at least 2.6 gram per cubic centimeter must be establishable. And of course, the catalyst must be scalable to larger amounts because they want to use it also in a technical scale. So now I have an example of a joint project which combines several groups of the institute together with industry partners and 3 other institutions from Bremen, Stralsund and Greifswald, but due to the time I would like to skip this now and stop here at this point. Thank you very much for your attention.
Thank you, Angelica. It's very impressive the facilities you have over there in LICAT. So thank you for the overview. And I'm opening the floor for discussion. So any questions for Angelica? Yeah, Melis?
Maybe this is not a fair question, but since we seem to have time, can we hear more about the Supreme project?
Yes, I have to ask our chairman. So perhaps not so much in detail, but yeah, so this Supreme stands for supporting climate protection from renewable hydrogen to aerobic CO2 and methanol. So what we want to do here is using non-classical methods to absorb CO2 and to hydrogenate it to methanol with the same catalyst in the same system. Non-classical, we call it because we do not want to use thermal energy to put into the system, but alternative energy sources such as plasma and photo. And these high entropy energy alloys are alternative catalysts. So it's an alloy of a huge amount of different metals, and it has been shown that such type of catalysts can hydrogenate CO2 to higher hydrocarbons, and we want to test it here if it's possible for methanol. And so we have this methanol synthesis at low temperature. We want to stay below 200 degrees C, and of course much below the usually used pressure in industry. And we want to remove the CO2 from air. This is another challenge because we have only ppm range of CO2 in air, and we use homogeneous and heterogeneous catalysis, mechanistic and structure reactivity relation studies, and finally we hope that we come to success. There is already some previous work, so it has been shown that this type here of Syria, of mixed Syria mixed oxides with these metals, these materials, they can hydrogenate CO2 to dimethyl carbonate, and this is an intermediate in the methanol synthesis. So we have the hope that we can perhaps skip this intermediate step when we develop these catalysts and finally end up in one step at the methanol. And the plasma it is known that plasma can activate hydrogen and CO2 already at room temperature because it's breaking bonds and creating a lot of electrons, and we just want to try to see if this plasma can help us here. So this group is developing a novel plasma reactor for performing this reaction with these type of catalysts. And then we have homogeneous CO2 mining. I have shown this already with these amine systems, and the ruthenium pincer complexes, I have shown you that these are able to do the reaction also, and we want to use other catalysts here. And then we have, of course, the catalytic tests at low temperature, and then we have this photocatalytic group which wants to use light to promote the desorption of intermediates. That might be a problem, that the catalyst surface is polluted by adsorbates, and they want to try to put light energy into and enable the quick desorption and to facilitate kinetics of this reaction. Yes, and our group, of course, we are looking with all our zoo of methods on these type of catalysts in these reactions. And then we have collaboration with a small industrial group and another institute, and they want to explore the requirements for this process and do calculation of efficiencies, and to support the development groups to drive this development to a scale where it could be technically used. So, And now it's really the end. Thank you for your attention. And this is a nice photo from the lighthouse in Warnemünde.
Maybe over the coffee break we can have more discussion with Angelica, so we can continue. Thank you, Angelica, very much for your kind presentation. Right. So we need to move on with the agenda, and the next talk is coming from United Kingdom, from Green Fuels Limited, and it's going to be presented by Sergio Lima, who is the research director in the company, R&D manager. So thank you, Sergio, for taking some time to be with us today. And whenever you're ready, the floor is yours.
So thank you very much for the kind invitation, Tomas, Anna Belén, and all the team from BIOALL for having the bold to invite me for this presentation. Obviously, we went through a lot of technical details, a lot of catalysis details, and I was struggling to think about what I would present here, and I thought perhaps I will not bother you with too many scientific details, but I will try to give you an overview of the challenges when we are planning to use waste and wet feedstocks for the production of biofuels, in particular for sustainable aviation fuel. And that is the goal for today. I will try to approach two different routes. One is call it fat to fuels, and the other one is waste to fuels. So, okay. So starting from aviation sector, obviously everybody is aware, and as we fly more often nowadays, we are aware that we need to tackle some of the challenges, and CO2 emissions, as everybody is aware, is an issue. The aviation sector is the fastest growing greenhouse gas emissions, or one of the most, or the fast growing sectors of that, with 4% of increase every single year. So which obviously if we don't tackle that can be scalable. And this plot is particularly interesting because it shows that if we continue as business as usual, we, basically by, where is that? I don't know if yeah, no. So by 2050, for example, we will need 852 million tons of SAF currently, okay? Obviously we can do something to decrease that consumption. We can improve technology, we can improve operations, we can add more technology and biofuels to reach a carbon neutral growth. So basically, and looking in particular to this challenge, recently in UK, it was approved a sustainable aviation fuel mandate, which basically is similar to what is been discussing in Europe anyway, but is a bit more ambitious than the European one, because they want to implement this mandate for using 10% of blend of sustainable aviation fuel by 2030. In Europe, I believe that is around 5%. So there is a lot of challenges, but when we are thinking about replacing completely paraffinic, heteroatoms-free type of fuel, like jet fuel, Jet A1 or Jet A, doesn't matter, we need to think about it, in particular for aviation. One of the key points is the volumetric energy density, right? So they use paraffinic fuels because basically they have a really high energy density, right? And a considerably mild specific energy. So if we look at jet fuel in this plot, it's quite on top and more or less in the middle. So when we think about replacing that jet fuel, for example, for electrification, like we see it every single day in the road transportation sector, it works quite well. Everybody wants to have an electric car, right? But when we think to a plane, that change is a bit more challenging because we need, for the same energy, basically we need to add more weight to the plane, right? And in the car is also that challenge as well, so it's not different. And if we are thinking about replacing paraffinic fuels to liquid hydrogen, we need more volume. So that is what we need to face. So for the same amount of fuel, jet fuel, we need 30 times more weight of batteries. And we need 4 times the volume of hydrogen, for example. And that is what we need to keep in mind when we are planning to fly right? So why biofuels today? Everybody is aware of the challenge that we are facing, climate changes, rise of temperature, more extreme weather events, which are tackled not only United States, as we saw recently in the news, but also Europe and South Europe. We are facing that as well, here in Spain, Portugal, and so on, and Italy. So there is obviously an urgency on that. And there is also some social responsibility, because we need to address our waste. We are the ones which have to clean up our mess. We cannot expect the others to clean our mess. And that is my message when I try to explain to my kids why we should clean up things at home. And I think that this works for everybody, including myself. I need to keep reminding me every single time that I'm in the lab that I need to clean up the lab bench and everything. So why sustainable fuels today? Well, obviously the markets, everybody knows that. The markets are driven by economics, by demand, right? If there is no demand, there is no value or potential value. So by 2050, it's expected that, as you can see, we are in more or less 2025, let's say, more or less. That is the demand which is expected for 2025. And look at how it grows 2050, right? So the demand for sustainable aviation fuel will increase, in particular because of these policies, which are being in place in Europe, United States, UK, so on, so on. But then, after that, it's expected to decrease. Why is that? Because technology will change, right? We expect, and we saw already in the recent past, some good examples of planes which are running with hydrogen. We are running, in particular for shorter distance, and electricity as well, with batteries, right? It's expected that that will take a couple of decades to reach to a point where actually the industry, the aviation industry, will also try to change and develop the technology and reach to the stage of maturity. So that demand will decrease over time. But until then, we need to look at this with detail, and obviously hydrocarbon fuels are needed, and the global market needs those. So the conclusion is aviation needs low carbon fuels. They have to include hydrocarbon fuels for the time being, and why not producing those fuels from wastes? So when we are thinking about waste, the first thing that we think about, okay, the easiest perhaps route to produce fuels is using a feedstock which is closer in terms of structure, in terms of properties, to the paraffinic fuels, right? Vegetable oils, animal oils, animal tallow, something like that, right? But looking to the waste in particular, for example, used cooking oil, it contains a lot of soluble and insoluble impurities, right? For example, when we are frying something at home, right? We can have chips on the used cooking oil. We can have remainings of meat. We can fish. We can have a lot of things. But there is a lot of insoluble impurities as well, which then will affect the upgrading of that oil to a paraffinic fuel. For example, free fatty acids, which is difficult to imagine, but we have triglycerides, which then they break down, and you have free fatty acids. How this is going to affect the overall performance of the catalyst, because they are basically increasing the acidity of the medium, right? Also, compounds which actually they cannot be converted easily into something which we can then produce the fuels. But what about the inorganics, which are soluble as well, right? Like phosphorus, like calcium, and magnesium. So here is a good example of different waste oils and the concentration in ppms of inorganic contaminants like phosphorus, like calcium and magnesium. As you can see, used cooking oil is not so bad, right? 27 ppm comparing with beef tallow, right? But if you think about it, in the refinery, and where they are used, where catalysts like nickel, molybdenum, or nickel tungsten-based catalysts, sulfide ones, they are used for the HGO reaction, which I'm not going to give any details because yesterday we had a fantastic, we had at least 2 fantastic presentations where they were particularly discussing the challenge of HDO. But for example, this catalyst, the first one, which is used for HDO, it is poisoned by phosphorus in concentration of 2 to 3 ppm. So if your stream, you have more than 2 or 3 ppm, you're already killing the catalyst, right? And killing the catalyst in a huge scale is not the same as in the lab scale where we use milligrams or grams, right? And the total inorganic contaminants for this particular catalyst cannot be higher than 5 ppm, basically. So transiffication is purification step. And here I'm trying to bring a bit of what we do at Greenfuels. I will talk a bit more about Greenfuels. So we basically look at, we sell biodiesel equipment, we manufacture them, and in particular to sell all over the world. But one of the key points for the production of SAF is the purification of these waste feedstock streams and how we could have a consistent intermediate which can be upgraded to a final fuel. So good transiffication reaction, the conversion of oil into biodiesel, a purification step, and this plot shows exactly the percentage of removal of these inorganic contaminants after the transiffication. Transiffication reaction is basically converting triglycerides into fatty acids into esters. And for that we need an alkaline catalyst and we need a short alcohol like methanol, right? And basically this is a homogeneous catalysis and it's quite straightforward. So it's a conversion of 100%, selectivity 100%, and basically you end up forming 2 phases, biodiesel and crude glycerol, which separates spontaneously if your moisture content in the oil is low enough, because otherwise they will not separate. And it depends also of the soluble contaminants. So basically, to look at this challenge, there is a critical pathway, which when I was addressing that, I thought, what are the possible routes to convert something like a waste oil into a biofuel? Well, there is obviously, when we start from a waste, and I mentioned that a couple of times, we need to consider pretreatment before any type of hydrotreatment, HDO, hydrocracking, and isomerization. Transiffication can be one possible route. The other one can be straight away from oil to HDO, doing some cleaning, polishing, as was mentioned earlier. Or we can just try to dilute those contaminants, blending. Okay? And that's the other way of doing it. But I put here something different, which was co-feeding, which is one possible route, standalone route, so as I mentioned before, and addition of short alcohols. And I will explain why I mentioned that later. But the critical point here is that we are trying to produce something, as I mentioned before, is heteroatomous free, oxygen free. And in this case, there is almost none nitrogen or sulfur because of the characteristic of this feedstock. But when we are talking about other feedstock, we need to address that as well. But the bottleneck step of this conversion is definitely the HGO reaction. So we need to achieve 100% of HGO conversion, because otherwise the oxygenated compounds goes to the second reactor or the second catalytic bed and they poison the catalyst, and end of story. Okay? So not going through too much details about HDO, but basically triglycerides, as I mentioned to you during the hydroprocessing, they are thermally unstable, so they decompose at high temperature. Then there is heterogenation steps. There is 2 potential routes for removal of the carbon. The direct HDO route, which is we end up forming water, so water will be present, by the way. And there is the overall decarbonization routes, which basically we lose 1 carbon. And it might not seem so trivial, one route or the other, decarbonization versus hydrogenation. Yesterday, Roberto mentioned about how relevant is to select the route, because this will affect the overall consumption of hydrogen, right? So it's not so different. It's not trivial when, for example, direct hydrodeoxygenation, we need 16 millimoles, or is the opposite. We need 12, and decarbonization we need 4 millimoles more. So, for example, in that case, it means that when we are scaling up this, decarbonization will consume more, 25% of hydrogen, right? And there is other competing reactions, which were mentioned here so many times, which I'm not going to address, but that is irrelevant, okay? And at the same time, we need to look at this from the yield point of view as well. Either the oxygenation, we are not reducing the number of carbons. Decarbonization, we are eliminating one carbon, okay? So this is important. This is an example which I brought that as a challenge for researchers, basically, because I didn't have time to go deeper. But basically, I looked at in a different project. I looked in a continuous process to basically either deoxygenate fish oil, and basically, I end up in continuous mode, having really low conversions, HDO conversions. Then I thought, based on my previous experience, I said, okay, perhaps the water there is affecting the overall availability of hydrogen, and what if I change that, adding a bit of an alcohol to increase the availability of hydrogen, to see if that is the limiting step. So I start adding methanol, because methanol is soluble with biodiesel. Biodiesel was the intermediate produced after the used cooking oil, okay? So basically, I end up getting these plots which are here, and as you can see, adding 10% or higher volumes percentage of methanol, we could decrease the temperature and at the same time increase the conversion, right? And that's what's quite surprising. I thought, okay, perhaps it's exactly that. It's the hydrogen availability in the liquid media which is affecting this. So then I thought, okay, what if we increase the chain of the alcohol? Would that affect significantly or not? And actually, it doesn't. I try ethanol, we try propanol, butanol, and it doesn't affect much. So what are the possible explanations for that? There is a lot of experts on operandum and the operandum spectroscopy and so on. I'm pretty sure that there will be a challenge with this. But one of the theories is actually there is a competitive degradation, either the oxygenation of the alcohols first, and that ends up creating different types of coke. There is a coke called catalytic coke, and there is the coke called thermal coke. Thermal coke basically occupies the empty voids between particles, between catalysts. And basically, once that you have there, you are decreasing the surface area, availability of surface area, and you are basically killing everything, because you will cover absolutely everything, okay? So actually, adding methanol, we were able to actually to extend the operation of the continuous operation from 3 days to 7 days without having to stop and regenerate the catalyst. And believe me when I say that the spent catalyst look way better than without, because without using any methanol, it was like a block of cement, basically. But that is a challenge. So in the overview of the SAF production, as I said, we have waste oils, we have transfication as a purification step, and then we have the hydroprocessing. And as an outlet, we have a mixture of hydrocarbons that then, after fractional distillation, we will produce the different cuts. We'll get the different cuts that we need. Obviously, the reaction conditions and the operation conditions to be used, if we are targeting one particular cut full, they need to be tuned, right? Because we will always end up forming the 3 cuts. So this is part of a project, research project. Is a funded EU-funded project. Call it Green FlexJet, and basically we are responsible for the conversion of the used cooking oil into SAF. And in this process, there is hydrogen involved, obviously, and the concept of this project was actually to use, for the first time, create an integrated system and a technology to be 100% waste dependent, basically. So use cooking oil, and the process to produce hydrogen is thermocatalytic reforming. Is technology which has been developed from Fraunhofer Institute in Germany and Birmingham University as well. So, but basically any green hydrogen can be used in this process. It involves 12 different partners between UK, Italy, Germany, and so on. So this project continues until March 2024 with a lot of challenges. But we need to keep in mind that when we are thinking about sustainable aviation fuel, in particular commercial flights, aircrafts and their engines are certified to fly only if the fuel meets tight specifications. And there is, because of that, there is standards, international standards, to guarantee that actually what is used is something which it will not jeopardize the flight when we are at, I don't know, 40,000 meters high and the plane just comes down, right? So when we think about jet fuel, we need to keep in mind that these are not only linear hydrocarbons. We have a lot of other stuff. And they are there for one reason, by the way. So we have cycloparaffins, we have aromatics, we have isoparaffins as well. And the most important is that these different families, hydrocarbons families, they will affect the fuel properties. For example, the specific energy will be dependent of the composition of the alkanes and linear paraffins. Energy density will depend of cycloalkanes and aromatics. And freezing point, for example, it will be really dependent of iso and cycloalkanes, aromatics. And aromatics, by the way, are there just to annoy us, because basically, from combustion point of view, they are a problem. But they are needed for legacy reasons. And they are there because to avoid seal leaks, full leaks. And that is the main reason why aromatics needs to be there, by the way. And aviation industry is quite conservative in changes, and we need to keep this in mind every single time that we are developing fuel, okay? And as I said, for example, if we increase the ratio of cyclic alkanes and isoalkanes comparing to the jet fuel, we are lowering the freezing point, which is also a good thing when we are high altitude, minus 40 degrees Celsius. So if the fuel start freezing, basically. If, for example, we increase as well the cycloalkanes comparing with the jet fuel, that's a good thing, more energy, right? And aromatics, they need to be kept at the lower concentrations possible to avoid the sooting, which is then will be an issue. Okay. Briefly about the internal standards to guarantee that actually everything goes well. So there is this ASTM D7566, which basically it shows which pathways for the production of sustainable aviation fuel are certified and which one are still in assessment. But basically, if you want to produce something which will have commercial value and will be safe to use in the plane anyway, you need to follow these routes, one of these routes. And these routes are limited to the feedstock that you are going to use and the technology that you are going to use. So if you are planning to use the same technology but a different feedstock, then you need to apply for approval of a new full pathway, which is a painful process and costly process. From among all the pathways, the most straightforward one is the FO1, which is the one which I presented before. Basically, oils to jet fuel is the less capital intensive and is the closest one which is in commercial maturity. So many refinery companies are planning to build sustainable aviation fuel plants, and they are going to use EFA basically. So we did some basic tests. So we look at the GC chromatogram and compare with jet fuel. I remember a nice presentation about using ICMS techniques to look at different compounds. As you can see here, it doesn't look too much, but if you perform a ICMS analysis, you will see, like you saw yesterday in the presentation of Roberto, hundreds of different compounds that you can expect on this type of fuels. So in summary, aviation needs low carbon fuels. They need to include hydrocarbon fuels, and they need to derive from sustainable sources. Now I'm going to talk, if I have time. Do I still have time? Yeah? Okay, let me know when I should be quiet. Okay, so now transition from fat to fuels to waste to fuels. And why is that? It's a question of feedstock availability, basically. I didn't mention in the previous slides, but the availability of used cooking oil and vegetable oils is really limited. Just to give you an idea, pre-pandemic, the price of 1 ton of used cooking oil was around, I would say, 300 pounds. Now, after pandemic, is 1,200 pounds, 3 times, 4 times more, just to give you an idea. It's because of the availability, it's because of the market is saturated, because if we plan to produce, for example, SAF from used cooking oil, we are competing as well with the diesel industry, and we are competing with other routes as well. So the amount of used cooking oil available is really limited. So the only way of moving from that issue is to look at alternative feedstocks. And why not something which we all contribute, which is waste sewage sludge. So this was part of a project, and is still part of a project. We are trying to scale up this technology and bring it to commercialization stage. The name of the project was called Firefly, and it was funded by the Department of Transport from the government of UK. It was funded as part of the Green Foods, Green Skies competition. The aim was to demonstrate a new technology route for sustainable aviation fuel using sewage sludge as feedstock and using hydrothermal liquefaction as key enabling technology. So basically on this project, it was an 11-month project, which ended up being 12. But basically during that time, we worked in particular with front-end engineering design, and that was the plan of the project, and for a demonstration plan and also a pre-feed for a commercial plan. And this was performed in collaboration with the YPC contractor, which is called Petrofac, and also with Cranfield University for the LCA assessment studies. So the Firefly solution, so as I mentioned, using hydrothermal liquefaction, sewage cake treated at high temperature and high pressure. Basically, we will produce biocrude, then we can upgrade that to biofuels, but he also produces other valuable byproducts, which I will talk later. One of the advantages, obviously, is that is widely available, is a low-cost feedstock, and basically there is also beneficial and social benefits to use this type of feedstock. So, and this slide is quite funny, but let's know our sewage, right? So sewage is a byproduct from wastewater treatment facilities. And that is what, after all the pretreatment steps, we end up forming what is called a sewage cake, right? And this is post anaerobic digestion. It's post the production of biogas, by the way. We tested several sewage during the wastewater treatment facility process, and we end up realizing actually the final product, which is the cake, is the best one in terms of yield of biocrude. So annually in UK is produced 57 million tons. So the population is increasing, by the way, which is a good thing for us. So that's how it should be. And basically another concern, environmental concern, is that the spreading of the cake, which was Until now, the main use of that is going to be prohibited. So it cannot be spread anymore in fields, okay? So we need to find a solution for that. And why not converting to biofuel, right? So just to give you an idea, in Europe, for example, 8.7 million tons of dry sweet sludge is produced per year, roughly. And each of us, annually, we produce around 20 to 25 kilograms of dry solids annually, okay? So this is quite easy to explain to every single person, which are not scientists. But we all understand that we need to go to the toilet, and we need to go every single us, right? So it's easy to understand from a process point of view to people which are not science related. So HTL, I will not go into much detail, but obviously is a thermochemical process which basically is less energy intensive than gasification or pyrolysis process, because in particular using wet feedstocks like this, like sweet sludge, which has a lot of moisture, we have to dry it first. In this case, we don't need to dry it. Actually, we need to add more water, because water will be the key ingredient to actually deconstruct the sweet sludge. We need high temperatures, we need high pressure, but the process is not only about selecting the temperature and the pressure. It's way more than that, because each feedstock has a different characteristics. And what we obtain is a biocrude, which is a really nice product which can be upgraded to biofuels. The problem is that it is composed by a lot of compounds which they don't want to be converted into hydrogen-free paraffins, which makes it quite challenges. And we have a really broad range of compounds. It has a lot of contaminants, it has a lot of nitrogen, it has sulfur, it has ashes, it has a lot of things which shouldn't be there if we want to produce fuels. So the challenge of upgrading this is thermal stability of the oil, is the high nitrogen content, high inorganics content as well, as I mentioned in the previous slides, the inorganics in particular, and the coke propensity. So when we are running this in continuous mode, for example, this is a tricky challenge, because clogging will happen. So it is possible to upgrade this biocrude. This is a good example which we obtained in the lab, really challenging. And we did some simulation, distillation analysis to the biocrude to try to understand how much of each cut, full cut, we can obtain. And that table in the bottom shows exactly that. So recently we acquired a micro automatic distillation system, which allows us actually to fractionate these really small samples and start looking to the properties of the jet fuel. So, but just to give you an overview about the simplified firefight process, how we envision this to go to the next stage, to the demonstration plant and commercial plant. So the sweet sludge has to be mixed with water, then goes to the, unfortunately I'm trying to see where is the pointer, but I cannot. I don't know, it's not. Where? Wait. Oh, there we go. Sorry about that. So we have the hydrothermal reaction. This is a continuous process, by the way. And then we have the separation, because we will produce 3 phases: the gaseous phase, the liquid phase, and the solid phase. I didn't mention about biochar, but biochar is a really valuable byproduct which accounts for the carbon negativity of the process. And this is particularly important. And also, it can be used as soil improver. And we are looking as well to that. I don't have time to give more details about this, but it's really valuable. So basically, the off gas goes to heat recovery unit, so burning and then released to the atmosphere. There is a separation. The biocrude, which is the valuable product here, will be pre-treated to remove a lot of most of the inorganic contaminants, basically, and then either treatment and fraction distillation, either cracking, then recycling, and then producing the stuff. So because basically, depending on the characteristics of the feedstock, as I mentioned before, you might end up having more of one full cut than other. So then you need to tackle this and trying to increase your yields. And this is the key point of this technology is that actually is not one of the approved routes for production of SAF. Didn't mention before, but when we are thinking about a new sustainable aviation fuel, this ASTM 7566, it not only specifies the characteristics of the fuel, which should be in compliance, but also gives you the maximum blendage of SAF with jet fuel that you can use as well. So currently, there is not such thing as using 100% of SAF in a plane, okay? At most, currently, it would be around 1 to 2% because there is no enough sustainable aviation fuel in the market. But at the maximum, for example, the air route, you can only blend up to 50%, and will depend, that blendage percentage will depend of the characteristics of the SAF. So if it's not one of the approved routes, you need to go through this ASTM 4054 qualification route, and this can take a couple of months, 2 years, and there is this clearance house in the United States which actually can help you in the process. They will do all the tests for you, and there is subdivided in tiers. Tier 1 for full specifications, properties, fit to purpose, and then you have components test and all this. So you might be lucky and you don't need to do any full tests in the engines if the engines manufacturer are happy with what they saw from the previous analysis. But you need to account this, and you will need gallons and gallons of fuel to accomplish that. That's exactly what we are planning to do in this route. So there is also something called pre-screening tires for assessing the potential of your sustainable aviation fuel for the next step, which is the qualification, the ASTM 4054, which is looking at more in detail into the properties and also using really low volumes. So, but this doesn't mean that if you are in compliance with this and it's fine, you are not going to fail in the other stage. But this is actually helps a lot. Sorry about that. So about green fuels, we were funded in 2003. As I said, we were a manufacturer of biodiesel units. In 2013, a new branch company was created to look at more into the decarbonization of transportation fuels. And that's what we have been doing at the moment. And this is in December 2018, we received the kind visit unofficially. He came to visit us because actually he used to live, I don't know if he's going to continue living there, but he used to live a couple of I would say 30 to 40 kilometers from where we are based. He has a fantastic farm, which I've been, because actually we supply him with bioethanol, because he has a really fancy 68 Aston Martin, which he loves to drive, and the engine was modified actually to run in E85, which is 85% ethanol and 50% gasoline, and we supply this fuel to him. So he knew us, and we have been in contact for many years. He's passionate about sustainability, about biofuels, and he came to visit us unofficially, and that is what I show here. Thank you very much.
Thank you so much.
Well, that was a very inspiring talk, Sergio. Thank you very much. I think we have time for one quick question, and maybe over the coffee we can discuss a lot with you, because Melis, you wanna, or maybe another quick one. That's fine.
Thank you for that great talk. I have a question about the fuel cost of transporting the raw materials to be processed in these ways.
It needs to be accounted, obviously, because one of the key points of this Firefly technology, for example, we thought about this from the beginning, because this is a key point, right? So how we envision this plant is to be located near the wastewater treatment facilities, exactly to decrease those costs. And having these decentralized plants spread all over UK, for example, or you might have, actually, that wasn't our initial thought, but is a question also of capex and how much would cost each plant and the size of it and all the economic constraints which we need to think about in advance. So, but how do we envision this? Is these plants be located in the wastewater treatment facility, basically avoiding transportation, but also one of the key points is that the HTL process will produce wastewater, which is another topic which I forgot to mention, but is a really interesting topic, by the way, because it has a lot of energy value there, because it has a lot of soluble oxygenates, which actually they can be used to produce green hydrogen using hydrothermal gasification, or biomethane, for example, or hydrogen, basically. And there is a lot of interest on that. And that's, but how we envision the simplicity of this process was actually to, as soon as the HCl wastewater was produced, send it back to the wastewater treatment facility because basically we are there, right? So that decreases as well transportation and decrease the capex of wastewater treatment facility, because in Europe, for example, this wastewater treatment facility has to be treated before being disposal, because it has a really high content of nitrogen, almost 25%, if I remember well, or at least more than 50% of nitrogen content, which was in the sewage sludge, ends up in the wastewater. So and this needs to be removed before sending the wastewater to treatment because of the ammonia, which then will be released. But in UK, that can be done in a more straightforward way, and that's an advantage as well. So we can actually recycle the water here in the process and just decrease that cost. But you are completely right.
Thank you.
No worries.
All right, we thank you again, the speaker. And we move on with the agenda. Just the last presentation before the coffee break is coming from the European Joint Research Center. It's going to be presented by Jacopo Tattini. Thank you, Jacopo, to take some time to be with us today. Whenever you are ready, the floor is yours. Oh, perfect.
Good morning, everyone. I'm aware that I'm standing between you and the coffee break, so I will try to be brief. Please let me know if I will not pass. My name is Jacopo Tattini, and I'm an energy analyst at the Joint Research Center of the European Commission. So we're actually based next to this venue. We are just 300 meters away. I can say that I'm basically the neighbor of the organizers of the conference, and that's why they've kindly invited me here to give an overview of what the Joint Research Center is, as many of you might not know it, and in general about also the research that we carry out there that might be of interest for this community. And I will also present some of the modeling results of the analysis that we do with our global energy system model. This is the agenda that I've prepared for today. I will start with a brief introduction of what the Joint Research Center is, and then I will talk about the relevant research that we carry out in the Seville site. It's the one I know the best, and so that's the one I'm presenting to you. And in particular, I will focus, as I mentioned, on the insights of our modeling activities. But I acknowledge that in the other joint research centers, which are disseminated in Europe, there are colleagues who carry out research that might be relevant for this scientific community. So in the end, I'm providing a slide with some links. And once the presentation will be made available, you can look into that. I hope you find it interesting. So basically, what is the Joint Research Center? The Joint Research Center is one of the Directorate Generals of the European Commission, and we are called the Service DG. What it means is that we don't have a political agenda. We try to help all the other policy DGs to develop their policies, so we work very horizontally. And we're often referred as the Knowledge and Science Service of the European Commission. What it means is that we make our scientific knowledge available in the policy-making process. So we're always consulted throughout the policy-making process. And I'm talking about scientific knowledge because we are in total 2,800 employees, and the vast majority of us are scientists and have a PhD. Here I'm presenting the organigram of the Joint Research Center, where you can see that our big boss is the President of the European Commission, Ursula von der Leyen. And then we work under the responsibility of Maria Gabriel. She's the Bulgarian commissioner. She's in charge of innovation, research, culture, and education and youth. But our work also fits in the area that Vice President Maros Sefcovic takes care of, which is called institutional relations and foresight. And our Director General is Stefan Quest. So in general, I told you we are in total 2,800 scientists, and we cover so many different disciplines, from nuclear safety to health to energy, which is the topic that is discussed today. And we try to help the policy making of the European Commission in any direction. So we work in a very multidisciplinary way, as I will explain soon. And as scientists at the Joint Research Center, we are, I would say, in a fortunate position because we work directly in the executive arm of the European institutions. So we are involved directly in the policy-making process. There's not a single policy process, where they don't reach out to us and when we are not directly involved. And I think this is very enthusiastic, and I think that makes a big difference because we get to know a lot of new things that working research sometimes we might not see. So that's why we're trying to communicate it here, coming to these type of venues, and I'm looking forward to receiving your questions and to get my point of view also on that aspect. Here is our mission. So as the Science and Knowledge Service of the European Commission, our mission is to support the EU policies with independent evidence throughout the whole policy cycle. And here I think we can extract some very important keywords. We are independent of every type of interest, and we are policy neutral. As I mentioned at the beginning, we don't have a policy agenda. So regardless of the country where we come from, regardless of our personal political belief, and if some of us were previously working in a company, we're not trying to promote any interest, but we're trying to be unbiased in this. And as employees at the Joint Research Center, we have three main purposes. The first one is to anticipate. So we try to look ahead what's going to happen, what are the upcoming challenges, what are the upcoming issues, to try to make the European policies resilient for that. And you can see a lot of challenges in that with the current situation in the energy sector, for instance, and the dependent on gas and Russian gas. Then we also integrate. What it means is that we connect the dots of very different scientific disciplines. So normally there are different departments that are involved in the preparation of the same policy, because we want to try to have a comprehensive view to make it resilient from several different points of view. It's not just sufficient one specific knowledge, but we need several knowledges altogether. And impact, because we try to measure the impacts of the European policies throughout time. Where are the JRC sites located? The headquarters is located in Brussels. That's where our Director General works. And then there are 5 centers located in different member states. We have Petten in the Netherlands, Geel in Brussels, Karlsruhe in Germany, Ispra in the north of Italy, and then Seville, which is, as I mentioned, is located really next to where we are now, just I would say 200, 300 meters from us. And I would like to tell you a bit more what is the research activities that are carried out here, but there is a universe outside which I don't know yet that well, and I think it's also challenging for our Director General itself, as you know, there are so many activities going on. The unit where I work is called Economics of Climate Change, Energy and Transport. And what we do, our mission is to create and maintain a pool of expertise in policy analysis that is related to energy, transport, and climate change.
And when I talk about these three topics and the climate change issue, it's important to take into account that we don't consider them as silos. But really what they've tried to do in this unit is to really build a holistic knowledge, and we analyze cross-sectoral synergies between the different sectors. We analyze the dynamics across the different sectors to try to come out with policies that take into account different points of view. And so in this multidimensional analysis, what we have done is that we have developed quantitative modeling tools that are integrated, and I will try to explain how this works with this chart. So we can see the two core models that are maintained in our unit are potential and pulse. Potential is an energy system model of the European Union, and pulse is an energy system model of the whole world. Then when we want specific insights about the dynamics in the electricity sector, we can soft link with METIS, which is a power dispatch model of the electricity sector. We have colleagues working on the macroeconomics models, computational general equilibrium models, which assess what are the impacts on the broader economy of transformation in the energy system. For instance, what is the impact on employment, on GDP, and the distribution of health, which now is a very important topic for the European Commission. We also can soft link the European, with the potential model with some specific transport models. The first one has a better characterization of transport technologies, and the second one TNET represents the European transport network. Then, with these energy system models, we are able to capture the impact on greenhouse gas emissions, on CO2 emissions, and we need to soft link with the Gaines and Edgar models to understand also the impacts on other greenhouse gas emissions, non-CO2 greenhouse gas emissions, and with air pollution. And finally, we have to take into account that about 15% of European emissions do not come from the energy system itself, but from agriculture, from the agriculture sector, and from land use change, land use change, and forest. And so we evaluate that soft linking with these two models, Capri and Globion. And I would like to talk to you about a publication, an annual publication that we developed using these two models, the PULSE and the GME3. And this report is called the GECO, the Global Energy and Climate Outlook. The Global Energy and Climate Outlook is basically a report that is produced annually and that evaluates what is the impact of energy and climate policies in terms of greenhouse gas emissions and temperature rise. It's quite an important one because it's the one that the European Union, the European Commission, uses when it negotiates with other countries emission reduction targets at the Conference of Parties. So the first time it was produced was for the Conference of Parties when the Paris Agreement was established, and since then we have had an annual update. The last one was for the Conference of Parties at Glasgow last year, and my colleagues looked into 3 different scenarios. They evaluated what is the impact of current policies. So if the current policy framework is going to evolve, it's going to remain stable, there are no new policies with respect to what is already in place today, what's going to happen? In the second one, they evaluate the case in which all the nationally determined contributions are fulfilled, and also in case the net zero pledges are fulfilled. And finally, the third scenario is a scenario which is consistent with the Paris Agreement. So first of all, I would like to describe you what are the pathways in terms of greenhouse gas emissions stemming from these 3 scenarios, and what are the implications in terms of temperature rise. Let's start with the current policy scenario, which is here indicated with the red curve. And you can see that if current policies do not change, we would see an increase of global greenhouse gas emissions up to around 2040, and then they would remain stable. They would plateau around 2040. And this type of pathway is in line with a temperature increase of 3.1 Celsius. What happens instead in case the national determined contribution and the net zero targets are fulfilled? you can see that with this blue line, basically this type of trajectory would be in line with the temperature increase of 1.8 Celsius. It's interesting to observe here just 2 years before, in 2019, when my colleagues carried out the same analysis, this curve here was consistent with 3 Celsius. So in the meanwhile, in just 2 years, governments have announced a lot of ambitious targets. But still, there is an issue here. We can see this implementation, we call it implementation gap. A big gap between what are the targets that governments have put in place and what instead are the policies to reach those targets. So basically, there are ambitious targets that the European Union, China, all the different governments around the world have put in place, but there are not yet the policies to reach those ambitions. And at least equally important, these targets are not in line with the trajectory that would bring us in line with 1.5 temperature Celsius increase, which is what was agreed in the Paris Agreement. So there is also this ambition gap to take into account. I'm an energy analyst, so I would like to present you a bit of things about, because big transformations in terms of global energy emissions will stem from transformation in the energy system. So what happens in the current policy scenario in terms of primary energy supply, we would expect that by 2050, the primary energy supply would almost increase with respect to today's levels. But if we look instead into a 1.5 scenario, so the one consistent with the Paris Agreement, we can see that we can reduce the primary energy supply, and this is going to happen mainly through energy efficiency. And here, very important is the role of electrification. But what happens? If we're talking about electrifying the end-use sectors like transport, residential sector, and industry in a climate-constrained world, it means that we are increasing the demand of electricity, but we have to produce it, reducing emissions. And here we can see some dynamics of what happens, that the consumption of coal must phase out. We cannot afford producing electricity and in general using coal, and it phases out by the end of the century. And there's also a reduction in the consumption of oil and natural gas, which completely reduces by 2060. And on the other hand, there is a slight increase in the production in the consumption, of nuclear, of biomass, which is very interesting for this community, and of all the other renewable energy sources. I would like to spend the remaining of the time to talk a bit about the technologies and processes that are most relevant for this group. And I will start with electrofuels. Here I have to apologize because in this edition of the study, my colleagues had not break up electrofuels in different type of electrofuels. So there's not a breakup in ammonia, methanol, Fischer-Tropsch. But in the new edition of the Gecko, which will be released around December, you will be able to see this split. So I encourage you to have a look. So what happens in the current policy scenario in terms of consumption of electrofuels? We can see that the consumption starts with around 2020. There is already some small consumption of electrofuels in the international bunkers. So this is basically international aviation and shipping. And the consumption in the end-use sectors, which is basically heavy-duty transport, only starts later on, around 2035, okay? I know these numbers don't mean much by themselves, so let's look what it means in terms of shares. International bunkers in 2070 will account for about 10% of the total energy consumption of international shipping and aviation, so quite a decent role, I would say, while they're basically negligible in the end-use sectors. What is important to observe is that when we compare the uptake of electrofuels in the current policy scenario with the scenario consistent with the Paris Agreement, they're basically different order of magnitudes. Please note really the different y-axis. I decided not to use two different y-axes, otherwise the left side was invisible.
But this is to suggest that if we want to be consistent with the Paris Agreement, we really need to scale up the ambition, the targets, and the work on these fuels. There is a lot of work to be done, and I think this is an important message for this community because you are working at the forefront of this sector. And well, in 2070, electrofuels will play an important role in a Paris consistent scenario. You can see that for the international maritime and shipping sector, they will account for almost 3/4 of final energy consumption. So they will be the dominant fuel. And still, they will have a minor role in the heavy-duty transport sector. That's basically because we see here a better role for electrification and for direct use of hydrogen. But it is an important case for the use in aviation, as Sergio was just mentioning, and also in the maritime sector. I understand that some of you are also working with direct air capture, so a couple of insights there. Here I've decided to show this picture, but I have to admit that it probably will get updated. Why? Because this is a very dynamic sector. There are a lot of announcements all the time. So you might have heard that Carbon Engineering, this is a Canadian company, has just announced that they will start in 2024 to capture 1 megatons of CO2 in the Permian Basin. And here instead we have, even in the current policy scenario, the uptake starts in 2035. So we will anticipate it. And similarly also the Swiss company Climeworks is developing a plant in Iceland. They already have one, but now they will start one which is 40 kilotons. So it's a very dynamic sector. But very big difference between current policies and what we need to do to be Paris consistent. In 2070, we need to capture every year 2 gigatons of CO2. To put into context, the European total greenhouse gas emissions from the European Union were about 3 gigatons in 2019. So basically, we need to capture worldwide almost the same 60% of the emissions that Europe emits every year. And also, looking at that with the geographical lens, we can see that, and this picture again might change, but based on the current status, the uptake of DAC will start in North America, and then it will propagate to Europe and especially to China. This in the current policy scenario, while in the Paris consistent scenario, we see a much more widespread adoption of direct air capture. I'm moving to my last slide, semi-last slide, sorry. It's a bit complex, so let me try to explain it. As I mentioned, my colleagues are also developing economic analysis to see the impact of transformation in the energy sector on the broad economy. And this is a figure that focuses on the impact on employment levels. So the width of the bar, the height of the bar, indicates the total level of employment in the current policy scenario in 2050. So the thickest is the bar, the more that sector employs in 2050 in the current policy scenario. While horizontally, you can see the variation of employment level in the Paris Agreement scenario compared to the current policy scenario. So basically, we have indicated in red when there is a relative reduction in employment level, and in green when there is a positive increase in employment level. Broadly, what we can see is that in a Paris compliant scenario, there will be a big shift of employment from the fossil fuel industry to utilities and in general companies that are related to electricity production and transmission, not just production, but also transmission. We need a lot of new networks. And also in the agriculture sector, not just for producing biomass and for collecting biomass, but also for managing the forest. There is a big component related to land use change and forest management. An important remark here, because you can see that in the 1.5, in the Paris Agreement scenario, there is an overall reduction, a relative reduction in employment level in manufacturing and in services. It's important to focus that this is a reduction in relative terms, but not in absolute terms. So compared to today, these sectors will employ more. It's just that they will employ less than what would happen in the current policy scenario. And the big assumptions behind this analysis is that the total employment level will be maintained. So my colleagues have not analyzed the effect on overall employment reduction, okay? The total employment level are maintained. And coming to the end, as I promised, I'm sharing here some links for you about other relevant JRC studies. I've tried to contact people around. They were not sharing as many as I hoped, but I'm also sharing with you my email, and you can reach out to me if you want insights on some projects. I can put in contact with the most relevant researcher. Here, I've already mentioned the GECO, and I told you in December we will have the 2022 edition, which will look into hydrogen trade. Potentia is the European energy system model I work with. We have developed energy outlooks up to 2050, and we will start doing it even later beyond. And you might have heard about the concave report. It looks into well-to-tank emissions for, I put here gasification, pyrolysis, and synthesis processes which are relevant for you. And also we have the CETO, Clean Energy Technology Observatory, where basically we update every year. We develop a market report for many technologies and processes, and we will have one on advanced biofuel and also one on renewable fuels of non-biological order. Here is my email, and thank you very much. Happy to answer to your questions.
Thank you, Jacopo. I believe your presentation is very timely and very inspiring for both academics and industrial colleagues, because we need to work close to policy making, and people like Jacopo is fundamental, really. So we much appreciate your contribution to this forum. And I open it up for discussion. Now we have time for a couple of questions, if anyone fancy. Sergio, I know, yeah.
Thank you, Jacopo. Really nice talk. My question is related with the current situation, madness situation, which we globally are facing about availability to energy, and how this could affect the predictions. For example, you show us a plot where you had different contributions, for example, from coal, the energy production from coal, and so on and so on. Obviously, everybody at the moment, because of these constraints with the natural gas coming from Russia or coming from other markets, how you predict that this will change completely the paradigm of energy supply in Europe, or how you see this moving forward?
Thanks, Sergio. So I would say I would tackle this question from 2 points of view. So in general, the current situation has brought the European Commission to enforce new policies that are being proposed. You know, the Repower EU has been announced in July, and so basically there are a lot of new, more ambitious policies in terms of accelerating the deployment of renewable electricity generation, also new targets in terms of hydrogen, of biogas, and this is just in the short term, but we are envisioning, we will probably hear anytime soon also new ambitious targets in the long term. This is the first step. Then what happen is that this must be converted, not just targets, as I mentioned, this must be converted into policies that bring us there. And their times are a little bit longer because we need also the Council of Ministers and the European Parliament to come to an agreement. But basically, as the situation has changed, the Commission has reacted quite fast in adapting to this situation and proposing new measures. So what we do is that in our current policy scenario, I work in the European, with the European model in particular. So we are constantly updating it depending on what the announcements by our colleagues in the policy DGs are. So basically, the situation has changed a lot, both because of these policies, and the other point is about the different geopolitical situation. What our projections for international fuel prices 1 year ago are completely off now. We have gas prices that have increased almost 8 times. So also here, this is one of the most important assumptions in energy system models like the one I presented to you, together with projections in GDP and population. So it's very delicate and it takes time to adapt it. because we need to go through the policy DGs, sometimes with International Monetary Fund. There are a lot of liaisons with different international organizations. But this by itself will drive some changes, and we expect also companies are reacting to it. I don't know if CEPSA itself, about this target of hydrogen, would have been so reactive and would have announced it so timely. Maybe they would have waited a bit more, but definitely we see also a response from industries. Industries sometimes are more proactive, sometimes are responding to policies, but both are moving faster in this moment.
Thank you, Jacobo. I think we're going to stop it here because we are just a little bit late for the coffee break, but I'm sure you wanted to continue this discussion over a relaxed cup of coffee. So thank you, Jacobo, again. And we have the coffee break just crossing the door, all right? And you guys in the background, been working all the morning, you are invited to come for sure. Please join us. Sí, ya, no, vamos a un pendrive, ¿vale? of. All right, guys, so just to continue with the program, next speaker is someone very familiar to me, myself, so it's very weird to be chairman and presenting, but anyway, so I'm gonna talk today about bio-waste valorization enabled by multi-component catalysts, just to continue with the beautiful discussions around catalysis and low-carbon technologies. The research I'm presenting today is coming from Surrey, although, as you know, which is linked to BIOALL project. As you know, I recently moved to Seville, where I'm doing most of my job. So that's why I don't need to present Seville, because you already see the city and it's a beautiful place. But, well, here we have Surrey also. So we have a beautiful campus, South England, right? So half an hour from London. Sunny and shiny, not all the time. In winter, we also have a little bit of strong winter sometimes. But still, it can be beautiful. Yeah, Angie, believe me, it's not once in a blue moon. It happens more than frequently that you know, right? Anyway, so you are very welcome to come and visit us under the framework of the BIOALL project. So the motivation of my talk actually has been kind of discussed already with the talks from Sergio, Juana, Roberto yesterday, also Nestor. Anyway, so decarbonizing the transport sector. And as Sergio was mentioning this morning, there are essentially two scenarios, right? Like the light transport scenario, which is our cars, our motorbikes, so something that very likely will go electric, at least for now, right? So that's why we have massive research on batteries and electrocatalysis, etc., and fuel cells. And there is the big question of the heavy transport. So what do we do with heavy transport? Do you imagine right now flying an aircraft with a battery? I would doubt it, right? So we still don't have powerful batteries, enough powerful to really run an aircraft or a ship. So for heavy transport, we need to rely on biofuels, right? And there is a big role that catalysis will play, as we've been seeing in the different presentations in this workshop. So we're going to discuss around this area. So biofuels typically should be produced from bio-waste, if possible. And I'm picturing here a typical example of a paper-making industry, right? Where we have this big issue with the residue, which they call black liquor. That residue happens to be rich in lignin. I think Roberto already gave us a masterclass on lignin, but it's a pretty complex extraction, right? So how to deal with lignin to really produce something useful from this residue? Well, standard technologies, and this morning Juana was mentioning that, we have pyrolysis, one of the technologies. Good, fine. You get a pyrolytic oil. The trouble is, as Nestor also mentioned yesterday, that we have a lot of oxygen in the pyrolytic oil. So that will resemble in detrimental properties like corrosivity, low heating value, immiscibility. So essentially, it's not a really good fuel, not even for blending. So we need to actually get rid of oxygen to make sure we can actually use that pyrolytic oil as a potential oil. So as I said, the standard technology is to remove oxygen, normally using hydrogen at high pressure, and a catalyst using a hydrodeoxygenation reaction. When I ask my students, what do you think is the most expensive part of this process? And as a catalysis person, I wanted them to say the catalyst. So I have room for me. But no, as Sergio is pointing, no. The most expensive part of this process is hydrogen, indeed, right? So I was having a look to Financial Times, and decarbonizing the United Kingdom, which is a tiny island if you compare to Europe, will cost £1 trillion. So we really need to find economically appealing options, really, to develop more economically appealing processes to get biofuels. So the idea here is, can we really get rid of hydrogen in this HDO process? And under the project that Laura was leading, actually, and also we have some funding from Chinese Scholarship Council to sponsor waste PhDs, we've been doing some research in this area, and this is something that Roberto normally likes. So where do we find hydrogen most in Earth? So the vast majority of hydrogen in Earth is stored in water, right? So the idea of this project was, can we really use water as a source of hydrogen so that we can develop perhaps, ideally, a multifunctional catalyst able to do first water activation to get hydrogen, and that hydrogen implemented in situ in the reaction? That was the question, with a multifunctional catalyst that can do 2 steps in one go. I'm looking at Sergio because this is also part of your forthcoming PhD, right? Good. So we started to try to prove this concept, and we make a start with a noble metal-based catalyst. Actually, we try ruthenium, rhodium, palladium, and gold using carbon support. By the way, this carbon was coming from residues as well, so it's eco-friendly catalyst, was recycling through a pyrolytic process, biochar activation of the carbon. Good. So obviously, you don't want to start with lignin. You can call me coward, but when you start doing catalyst design, you rather start with a model compound. So we started with guaiacol that has 2 oxygens, and it's good enough to prove the concept, to see whether we can remove oxygen. Good. So that's the overall process. We got guaiacol, and we are going to put it in a high-pressure reactor and see what do we get. Well, I don't going to bother you too much with the chemistry, but essentially the catalyst, noble metal-based catalysts, are very well dispersed. So we have good dispersion of the active phases on the carbon support, which is looking promising to do catalysis. So let's put them in the reactor and see what happens. Good. So we put them in the reactor, and as you will see over here, under 250 C, and sorry, the condition should be here, 250 C and 80 bars of pressure, we got up to 25% of conversion with ruthenium-based catalyst. And you may tell me, Thomas, 25? Sergio presented today 85% conversion and more when you have hydrogen in the system. And that's true. But we are using, remember, water as a hydrogen source. So even though it's a humble conversion, it's a breakthrough because we are actually getting closer to something that is promising for bio-oil upgrading in hydrothermal conditions, right, with water. Actually, when we look at the literature, we try to propose not a mechanism, but a reaction scheme to see whether our product distribution kind of follow up what the literature was saying. And actually, it does, because the most advanced products we get is phenol, the red bar over here, which is actually almost the very last step from guaiacol to benzene. That would be our last target, right? So we are getting close to get fully deoxygenated products using this technology of hydrogen-free HDO with noble metal-based catalyst. Now, obviously, you need to recycle the catalyst. I remember Roberto mentioned he made his PhD student do the cycle 10 times. I think I've been gentler than you, and I only 3 cycles, but to be fair, at the 3rd cycle, we already have a little bit of the activation. But we consider that as a proof of concept study, this kind of does the job. So we have something that can be recycled twice, almost 3 times, and with a little bit of activity and selectivity to the oxygenated products. Big problem I faced when I wanted to publish the paper to prove the concept and put as this is what we are doing. The referee was really asking for the hydrogen source. He said, listen, Thomas, I don't believe you're getting hydrogen from water because you have also a carbon support. And carbon, as you know, is full of functional groups. So you may have hydrogen from that carbon. I said, big question, good question. I'm gonna test my hypothesis then. So we did a TPD analysis of the carbon, just heating up our carbon in an inert atmosphere and following up mass number 2, which is hydrogen. And indeed, our support released hydrogen, but it releases hydrogen at 350 C. And my reaction is conducted at 250. So we discard 100% that hydrogen is coming from the support. Fine, but not good enough. We were more ambitious. So actually, why don't we do a real test? So we test it with deuterated water. So we use isotopic tracing to actually replace standard water and monitor whether we have a hydrogen exchange between our reactants and our reaction media. We monitor essentially the main products, phenol, catechol, and guaiacol, and I'm very happy to say that we did observe fully deuterated phenol. So we do have a hydrogen transfer between our reaction media and our products and reactants. So hydrogen definitely should come from water and is participating in the reaction. So as I said, promising result, only 25% of conversion, but at least we proved the concept. The next question in the table is obvious. So, Thomas, you've done that with noble metals. Fine. can you really get rid of noble metals and offer us something cheaper? We don't have a mine of ruthenium like in Chile you have, guys, so we need to find something cheaper, right? So, okay, we try to challenge ourselves to design multifunctional catalyst, multi-component catalyst, sorry. So instead of using ruthenium, we were going to go for nickel molybdenum, a combination of a bimetallic material. We keep carbon because we think carbon was working well in the previous study. So, and we have molybdenum, which is highly electro-oxyphilic, so it helps to activate oxygen-carbon bonds. And we put ceria also to promote also activation of carbon-oxygen bonds in ceria-oxygen vacancies. So we tried this multifunctional catalyst. And as you can see, we managed to match a little bit the behavior of the ruthenium catalyst with 23% of conversion. So in theory, we can replace this noble metal-based catalyst with transition metal multi-component formulation. So, well, this seems to be working. Fine. Well, the catalysts are stable, so pre and post reaction, as you can see, the dispersion is very similar. We have to admit, we have to be honest, we have a little bit of leaching under the reaction conditions, so we lose a little bit of, I see Sergio laughing, yes, we do, because it's a very hard environment, it's high pressure under hydrothermal condition. But they are kind of, we don't have sintering, but a little bit of leaching. Good, so I think we published, I would say, almost the very first papers on this area of hydrogen-free HDO, which is, I would say, an area worth exploring. And yeah, we keep working on that, and at the moment we have also new students working on that, like Sergio recently got his fellowship, so looking forward to see what's coming in the next 3 years. And well, the next challenge will be, Thomas, model compounds, really? Can we do something real? And yeah, we are going to do something real with lignin in collaboration with Imperial College. Roberto, you will apologize me because it was a collaboration with Marcos and Klaus, but well, for obvious reason, I spent time working with them. And in particular, we use sulfur-rich lignin, which is craft lignin, which is one of the rubbish ones that you don't want to work with. Fine. So how do we actually endeavor this challenge with sulfur-rich lignin? Well, we took an approach using supercritical water that some of our colleagues mentioned tangibly in their presentation. Supercritical water is an interesting reaction media because when water reaches supercritical point, it inverts polarity and it becomes a very good solvent for organic molecules. That means that you can have a very nice contact reactant catalyst, also avoiding mass transfer limitations because it's very well dissolved. Your big molecule, your big organic, is going to be very well dissolved. So that was the approach. We will use supercritical water and see what happens. An extra advantage of supercritical water is that it typically has this cage effect that encapsulates radicals. That's what they say in literature. I haven't proved that, but I'm going to tend to believe literature for once. So they encapsulate radicals to avoid recombination and cocking. So that's another extra plus of supercritical water. Good, we put the catalyst in a homemade reactor. We call it microbomb. It's really a microbomb because it's only a 20 milliliter reactor, this tiny, but it can go up to 300 bars. Actually, you need really high pressure to get supercritical. So we test it in the microbomb reactor. Obviously, when you use a real feedstock like lignin, the analysis becomes droughful. So you need to deal with solids, liquids, two types of liquids, aqueous and organics, and obviously you need to quantify solids and gases. Right, here we keep working with carbon for any reason. I think since I met my wife right now, I went into carbon catalysis because I was not a carbon guy at all, really. But anyway, I ended up liking carbon. So we put a carbon nanofiber and an activated carbon using nickel as an active phase and ceria as a promoter. You can see beautiful shapes for the nanofibers based catalyst, and here the activated carbon. Good. If you see what happened under supercritical water, we start with some materials with a very high surface area, and after a few minutes of reaction, the surface areas almost disappear for activated carbon. Why? Because supercritical water is a very aggressive reaction media, so you're really damaging your catalyst. However, the nanofibers are more robust, and they kind of retain very similar values of surface area. So they are looking more promising. When it comes to leaching, which is another problem we saw in HDO, again, Leaching with activated carbon is dramatic. You go from 10% of nickel to 3%, so you lost your active phase. So this is not a good news for a catalysis development perspective. However, when you have ceria in the formulation, ceria plus nanofibers, you retain your initial nickel loading. So that means that somehow ceria is stabilizing your nickel. There's a close interaction to remain in the catalyst after the process, so despite the supercritical water. Good. So let's have a look to the results. I'm not going to go into details, but essentially, when you treat lignin at supercritical water, you get a mixture of hydrophenolics and methoxyphenolics compounds. And as you can see in the color bars, the product distribution heavily depends on the catalyst you use, nanofibers or activated carbon. Fine, that's good news. This is how the ICMS looks like, so it's really a nightmare to interpret and to quantify. Some of our colleagues here in this room have a lot of experience, more than me on that. But anyway, just to showcase that this was something commendable, really, commendable. But actually, not only in the liquid phase that was our initial target, we also look at the gas phase. And we were surprised because in the gas phase, we also got some interesting products like hydrogen. So, well, that's an extra added value to the process. We managed to get some valuable liquids. I will show you now the composition, and also some gases, including hydrogen. Good. So when we do the mass balance, and I was expecting really to close the mass balance something around 60% for the PhD student. That would be for me more than enough considering the complexity of lignin. Happily, we got very close to 90%, some cases 80% to close the mass balance. That to me is a big achievement anyway. But the interesting point is that carbon remains mainly in the liquid phase. That's interesting because it can be a potential biocrude or a potential biofeedstock for further upgrading. But even more interesting, Roberto, you will like that, sulfur goes to the gas phase. So sulfur, you can retrieve sulfur from your craft lignin and send it to the gas phase, which is an easy way to separate it from your biocrude and get something more interesting in your liquid phase. So that was a very interesting technology to get sulfur-free bio-oil. And in summary, just to say that supercritical water is a reaction media worth exploring, despite the harsh condition, and despite it's very damaging also for the reactors, I must say. But anyway, it's something that can really help to deal with complex feedstocks like craft lignin, for instance. Good. We move to the biorefinery concept, which is something we've been discussing about, and in particular, under Elhan's thesis, she's already a doctor, she graduated a year ago. We wanted to, well, I always said that this kind of scenarios, biorefinery, using or trying to harness sun energy to implement it in the biorefinery is the frustration of the catalysis person, because we never managed to design a catalyst with the same capacity of this photosynthesis process can do, where they use CO2 as a carbon pool to do essentially everything. So we said, this is frustrating, why don't we try something in between? So instead of going to biorefinery, we tested the concept of hybrid refinery, which is essentially including bioprocessing units into the standard petroleum refinery. Why not? I mean, there is some advantages on this, because essentially you can take advantage of the infrastructure, which is already in place. So Juana, they have reformers, they have hydrocrackers, FCC units, so we can actually use those units to process some of the bio units. By the time we did this PhD project, we actually focused on willow and algae for sake of interest of the UK government, that we are actually pushing forward this strategy. And we focused to obtain these products, acetone, ethanol, butanol, the so-called ABE mixture, which has some commercial interest. Well, traditional ABE mixtures are produced from sugar with highly efficient, as I said, nature always does better with bacteria, right? You have Clostridium that can produce in a fermentation process ABE. The next step, natural in chemical engineering, would be separation. So if you want to do separation of this process, you will need a system of multiple columns, which is expensive. So our question was, can we avoid separation and actually do process integration and do condensation, catalytic reactions to do condensation and get long-chain hydrocarbons that might be useful in transport sector, for instance? That was the hypothesis here. And to validate the hypothesis, we went first to literature, and we saw that, well, something on these lines were already ongoing in Germany. Some colleagues working with expensive noble metal-based catalysts. At that time, I didn't have too much money in the team, so I wanted to research again to transition metals, right? So we designed, again, multi-component materials using iron, nickel, and copper with acid and basic sites because both are needed for the condensation reactions. And we decided to do a high pressure process in a par reactor to study the condensation of this ABE mixture and see whether we can get interesting products. Right, so in all the cases, the process is much better with a catalyst than without a catalyst. And if you see the selectivity to C2 to C7, C8 to C15, we get up to 90% selectivity, for instance, with the iron-based catalyst. Well, this is actually promising. So we demonstrate we can get high conversion, and we wanted to make some very basic calculation, basic numbers. Please, Jacobo, you apologize me for the very simple, not a techno-economic analysis at all, just simple, rough calculation. So how much money we put in the reactor, in our mixture, we put around $100. How much we can get in the best case scenario, considering the selectivity values we get with the iron catalyst, up to $700 per kilo. Actually, because we are getting some very expensive products, like 2-heptanone, which is pretty expensive. So that's the reason why the balance looks like that. So we have a significant increase. But beyond, let's say, the market value of our products, we also calculate the reduction on CO2 emission when we compare the hybrid refinery processes with the traditional chemical fossil fuel process. And we got that we can actually decrease our emission up to 34%, which, if you want to put, again, dollars into the equation, you just need to multiply that reduction to the CO2 tax we were paying back in 2019, and you get a reduction of 12K per ton of chemical produce, which can be significant depending on the scenario. We obviously put a patent on this process and the material, and we are working with UK companies actually to push forward the commercialization of this technology. Good, so partial conclusion so far. Anna, you tell me the timing because I'm not controlling the time anymore. I'm fine, I believe. I speak too fast. As I said, my student, you listen too slow. So anyway, partial conclusions. Hydrogen-free HDO is actually a promising technology to explore for bio-oils upgrading. The ABE strategy, actually moving not directly to biorefinery, but perhaps something in between, a hybrid refinery, is something that is worth exploring and is also within the context of this BIOALL project. So why not keep researching on these directions? And I'm gonna finish the presentation with the gas phase because all I've been talking about is liquid phase, which my PhD advisor sitting down over here, we said, Thomas, this is a scenario where you don't feel very comfortable because I educated myself in gas phase, all right? So I'm gonna briefly talk about gas phase because otherwise I would spend here 1 hour talking about CO2, and this was about bio-waste. So which bio-waste we can find on gas phase? Biogas, I think Sergio mentioned briefly this morning. Well, what are the standard technologies to do something with biogas? Heating. So you can combust it and use it for heat and power. Fine, it can work, but you still have some CO2 emission associated. So can we do something better actually with biogas? And obviously from a catalysis perspective, why not making a reaction between two greenhouse gases, CO2 and methane, and get something of value, which is syngas? This reaction is well known actually in chemical industries, called dry reforming of methane, and we can perhaps get to syngas, and with further upgrading with Fischer-Tropsch, we get fuels for localized, or even better, as Joanna mentioned this morning, delocalized applications, because biogas may come from small farms spread all over the geography in a particular place. Good. Well, challenge of DRMs are here actually. Before we go to the lab, I tell the students, let us do the thermodynamic first and see what happened, right? That's why I didn't get the ERC, Roberto. I didn't do thermodynamics. I didn't follow my advice to my students, but they did the thermodynamics for this reaction. And actually, if you see thermodynamics, this reaction is very endothermic. So the high yield you get high yields when you go to high temperatures for hydrogen and for CO. That means from the catalysis perspective that you need a thermally resistant catalyst to avoid sintering, okay? That's that on the one hand. But also, if you see the purple line over here, this is carbon. So you have carbon in all the temperature ranges because we have parallel reactions. So your catalyst must be able to, 1, tolerate sintering, 2, avoid carbon deposition. Right, so how do we deal with that? We can use noble metals-based catalysts. I'm back to my previous situation. We didn't have too much money, so we are gonna go with nickel. And you will tell me, Thomas, no way. Nickel is the one that suffers for sintering and carbon deposition always. It's textbook. Well, then here's the challenge. The challenge is to design a nickel-based catalyst that can really overcome carbon deposition and sintering. And under the PhD thesis of Estelle, now working in a British company, Ceres Power, we actually developed a nickel-based catalyst in which we actually protected nickel in an inorganic matrix, which is a pyrochloride structure. It's a mixture of pyrochloride perovskite structure in which nickel is kind of protected and can overcome these problems. And I will show you in a minute how. So we tested this nickel substitute pyrochlor with different quantities of nickel, 2%, 5%, 10%. And as you can see here, when you reach to 10%, you get very high values of methane and CO2 conversion. So this is promising, and we've been running for 30 hours, so it's looking like a robust catalyst. But 30 hours is not enough if you want really to put a patent or to talk to someone in industry. Even this test is not enough, but it's the best we could do in a lab. So it's 2 weeks running. So for 2 weeks, a stability test, 350 plus hours. And we have a very, very stable catalyst, just a little bit of the activation. I will tell you why in a minute. But the important point is that we can actually upgrade biogas mixtures, model biogas mixtures, and deliver syngas with a syngas ratio close to 1 continuously with this robust nickel-based catalyst. Good. We made some numbers again, and to reach this level of performance with a nickel-based catalyst like us, you need to pay around $2 per kilo. Some catalysts in the market already doing dry reforming based on rhodium or ruthenium, you need to pay up to $1,000 per kilo. So obviously, we also put a patent on this material, and happily, we are actually working on commercialization of this technology under a new spin-out company from Surrey University, which is Green Gas Catalyst Ltd, and seeking for collaboration. I believe the first one is going to be with Sergio, because we already have some conversation on this matter. So hopefully, we can push forward this technology at perhaps some commercial level. But someone doing Fischer-Tropsch will tell me, Thomas, syngas ratio 0.9, this is not good for Fischer-Tropsch. You need something hydrogen richer, right? So question was, can we really push hydrogen concentration in the syngas mixture? And again, we did some thermodynamic calculations, and it turns out that when you add some water in the reaction, you are doing actually B-reforming, steam and dry together, then you can actually push the hydrogen to CO ratio. We did that actually in collaboration. Estelle actually came to Seville in 2018 to work with Jose over here, and we did the reaction using some water in the reactor. And we saw that actually we can get up to 2.5 hydrogen CO ratio. Very good news. But life, unfortunately, is not so beautiful, because your syngas is improving the quality, but your conversion is decreasing. All right, so there is a penalty to pay. So we always said that if you want to go, you need to compromise. If you want pure carbon capture utilization, CCU, you go to dry reforming. But if you want to improve the quality of the syngas, you need to consider some water in the mixture, B-reforming. An extra advantage, I think, Jose, we were talking about that yesterday, remember, over a glass of wine. An extra advantage is that with B-reforming, when you put water, you totally eliminate high carbon deposits. So your catalyst can run for long periods. So that's very good news. And actually, we need to make some techno-economic analysis to actually check whether this is really a valuable option. So in collaboration with a very good friend of mine, Francisco Baena, who is now in Stockholm, in Chalmers, and hopefully coming back soon to Spain, we did a very, very light, we call it light techno-economic analysis, considering the cost, capex, opex of the steam reformer, natural gas prices, hydrogen cost, CO2 penalty, etc. And very depressing news for us when we started this study, because in all the scenarios we consider, the cash flow was negative. So this is not going to work ever. Wait, well, there is some hopes, because in the last scenario, when we consider the projected value of the emission getting very high, you start to see some profitability. So maybe it's not a technology for tomorrow, but it can be a technology maybe in 10-year time. So why not? We could do some research in biogas upgrading through catalytic processes. Well, I'm going to finish up. I believe I'm on time, right? Yeah, perfect. So we are working actually in circular economy, developing catalysis for these topics over here, biowaste, CO2, also hydrogen, and plastics that actually Melis presented yesterday very nicely. Our team, and in particular working with Jose, we try to go, we said from electrons to reactors. So we develop fundamental catalysis at electronic level, and then try to put the catalyst in a reactor, sometimes in a microchannel reactor, to do process intensification. I want to just send a couple of home messages for for the young people over there. Interconnection between chemistry, chemical engineering, policy making, industry, academia. So our travels, CO2 travel, biofuel travel, are not isolated travels, are global problems. So we need to collaborate, work together, okay, guys? And obviously the most important one, as the big professor used to say, don't lose your curiosity, right? So keep researching, because you must be a curious researcher to really push forward knowledge. Good, I want to thank the Catalysis team at the University of Surrey. They are actually the real artists, because they've done all the job I presented today. All of them are graduated, so I'm very proud of them. And obviously my Catalysis family. It's a pleasure to be back home, actually, after so many years as an immigrant. That's what we do, Mediterraneans, we need to emigrate. But I'm back home, and thank you, Jose, thank you all the team, Esbeth, my scientific mom, Luis, who is a fantastic partner all the way since I arrived. Luis, I owe you a lot, you know that. And well, we are gonna have lunch in this beautiful place, so I hope you, Enrique, don't come back to Alicante, stay, because we have beautiful views of the river. Come on. Right, any questions? I'll be happy to take it, and obviously let's keep collaborating over BIOALL.
So, thanks, Thomas. Is there any question? I like it that you said that you ended loving carbon. I said it yesterday also. It was for personal matters, maybe in your case, but...
I ended up loving Laura, and she gave me no choice.
Yeah,
so.
I know. I have to say I hated during my PhD, so if my PhD supervisor is connected online, I hated it by now. It changed. So, is there any question for Thomas?
Thank you, Thomas, for this really entertaining presentation. Your H2O with water is really fascinating, but I have a question on this. You told that you used D2O to ensure that really the hydrogen is coming from the water, and then you mentioned that the product was totally deuterated benzene. How can this be?
Not benzene, phenol.
Ah, phenol. Oh, then. Sorry, then I did...
It was my bad going too fast, sorry, Angelica. Yeah, but so it was a very good point indeed. Not benzene, it's
anyway, I want to ask this question. How can you ensure that you do not have a deuterium-hydrogen exchange just in the system?
I cannot ensure that.
But when you cannot ensure, how can you then be so sure that the hydrogen is really coming from the water? So
well, there is for sure a hydrogen transfer from the hydrogen media to your products, because we saw that in the mass spec. We could have also some non-deuterated products. I haven't said that, but that's a fair point. So let's say, as I said before, we have a new project for 4 years to continue working on this area, because it's still in NAPIs, very preliminary. But yeah, as I said, I cannot guarantee that all the mixture is deuterated. No, but part of the mixture for sure, because we saw that in the mass spec.
Okay,
thank you.
So, well, one more question,
Quickly. I have no problem with noble metal catalysts, by the way.
All right,
expensive. I have no problem whatsoever. I work in the past. I love them. But every single time that I see heterogeneous catalysts being used in the liquid phase, it comes to the crucial question of homogeneous contribution versus heterogeneous contribution. And that's what I always ask to my previous students. Have you checked that? What are your thoughts on this?
You reject that, you said?
No. What I mean is, you have leaching.
Yeah.
I
remember a discussion with you when you told me about Graya Ganchi's discussion. Exactly. We were about to play football in Hyde Park, I remember.
And you
so
were driving mad because of
the homogeneous contribution, because you've got a lot of noble metal ions in your solution.
Which is not a problem.
No, yeah.
You recycle them.
Exactly. That was my answer, actually. If you manage to recycle, fair enough. Job done.
Thanks, Thomas. I think we can move on.
Thank you. Thank you very much. And to continue with the agenda, we are going to move on to the next presentation. It's coming from a company, Greeny, a Spanish company. It's going to be presented by Enrique Montiel, who is the research manager at Greeny. So thank you, Enrique, for making time on your busy agenda. to come with us today. The
Okay.
floor is yours.
Thank you, Tomás.
Oh, reparar. Ahora reparar, ¿qué pasa?
¿Lo decimos reparar o...?
Sí, reparar. Habilitar. Ahora aceptar y habilitar.
Aceptar. Oh, tío.
¿Te ha movido?
Lo ha destrozado.
¿Quieres que usemos el mouse? ¿Puedo pedir que lo usemos?
O la volvemos a mandar. Todo.
¿Sí? Rafa, this presentation was coming from a Mac computer. Maybe we have an issue with the compatibility. We can try with the Mac otherwise.
Yeah.
El adaptador de Mac haya tenido problemas y no funciona.
Te hago la agenda. Vamos a preguntar. Krista, so if you don't mind, maybe we need to swap the agenda. Yeah, fantastic. All right, so the next presentation is coming from Elvesis. It's a company which is part of our BIOALL project, and with pleasure for us to receive Krista Ivanova representing the Elvis team. So, the floor is yours.
Like this? Okay, excellent. Okay, yeah. So, so I mentioned already it's not a very scientific presentation. It's more about our company and microfluidics in general. And I will give some examples of our participation in European projects and basically how an SME and a technological company can participate in collaborative projects. So to begin, I'm just like 1 second. I will escape just for 1 minute. Sorry about that. Just to make sure that it's the good presentation. Yes, okay. Yes, this is the slide I was aiming for. No, it's not this one. Yeah, my Spanish is not that good, so I'm trying to find the right this one it is, yes. Okay, so that was the slide that I actually wanted to start with. So to give you a little brief overview of our company, It was created by 3 researchers in Paris that graduated from the PhD, started the postdoc, and decided that they want their research to have a higher impact in general. So they did not want to focus on research projects from fundamental research. They had the idea to develop solutions that could have an impact that could serve not only their own project, but projects all around the world, and to accelerate research in general. So our CEO himself, that's Guillaume, who you see on top right. So he was from the beginning one of the founders of the company, and he's still there today. So the company was founded nearly 10 years ago, so a little bit over 10 years now. And in the beginning, there were really 3 people that were working on basically developing instruments for research. And it went so well that today we have approximately 50 people. And we continue with the same mission, like right from the beginning. And so basically, what is the company about? It is about microfluidic instruments and equipment. I will go into that technology a little bit later. So we produce the instruments on site in Paris, and we sell them to customers all over the world. But in parallel, we also participate in research projects where we offer these instruments and further developments on that technology adapted to specific projects. But always with the view that this technology that we develop could serve other purposes and other applications as well. So what is microfluidics in fact? It is a system that uses pressure to pressurize a reservoir, which in fact is a modified Falcon tube. So if anybody has worked in a research laboratory and has used basic laboratory equipment, they know Falcon tubes. So it's Falcon tubes that have a modified cap. So you can insert pressurized air and basically push out the liquid from the reservoirs and into a specific system. And then again, what is the final application? It depends really on what you want to do. We work a lot with cell culture, for example. So a lot of our applications are based in biology. So you can, for example, cultivate cells on a microfluidic chip, but you can perform other things. So basically everything that would require the controlled injection of liquids into your flow cell. So just a very brief overview of our structure. We have one unit that deals with the production and marketing of the instruments themselves. So it's really the company side. They have the marketing, sales, R&D and production. And we have the innovation unit where I personally work, and we basically work on collaborative projects. And the idea is that developments coming from the innovation unit in collaboration with researchers give an output that is so valuable for the community in general that they can then be transferred to the production and to the R&D of ElveFlow and yield real products that can be then also marketed to customers. So again, it's just really a brief overview of what we have. So we have basically the on-site manufacturing, supply, everything in Paris. We also have basically all of the teams required for ElveFlow. I will not go into that too much. I will focus on the innovation unit where we work on the projects. So we have approximately 25 people on site at the moment. We also participate in Marie Curie ITN projects, formerly ITN, now doctoral networks. So we have PhD candidates working on site at Elvisis in collaboration with the university where they obtain their PhD degree. We participated in the past also in the postdoctoral fellowships and in RISE projects, and we have also projects from Horizon 2020 or Horizon Europe ongoing. So our role in those projects is always to propose a microfluidic platform and development that is, as I mentioned, adapted to the project. So as a very brief overview of projects where we have participated in, I can mention, for example, PAN-BIOALL, which was a microfluidic platform for the safety assessment of biomaterials. So they would have mammalian cell culture and also bacterial cell culture and testing basically the toxicity of novel materials. Or org therapy, which is a project that wants to reproduce the spinal cord in a microfluidic system. So they have a 3D printed matrix, embedded cells, and perfuse this matrix with medium to keep basically the cells alive and to induce differentiation. Or Project Electromed, which is actually a platform that synthesizes peptides in a very controlled manner. So in this case, the injection of liquids would contain the peptides, which would be added in a pre-programmed way, so that you can synthesize peptides with a specific sequence. And so that's just a very brief overview of our facilities. And I wanted to mention, so our participation in Project BIOALL would be to miniaturize the chemical reactions and to create sort of microreactors. So that would be, basically what we can offer for this project specifically. And that's actually the end of my presentation. So it was a very brief one because I also thought we are all waiting for lunch, so probably it's easier. So I'm also going to participate in the lunch. So if someone wants to discuss later on microfluidics, I'm also there. And if there are some questions from the room, you're more than welcome. Yeah. Thank you.
So, any questions for Krista?
I have one. No, well, really, I do like too much microreactor and microfluidics. Do you have all your material glass-based reactor, or are polymeric, metallic, or what?
Yeah, so basically the bioreactor itself or the flow cell itself can be made out of whatever material you want or need. We don't manufacture the bioreactors ourselves. We work in collaboration with partners that produce these flow cells because they are very specific for different projects. Some need to be, with channels, some are basically chambers, some are coated, some have membranes. So it's very specific development, and it's a whole other expertise. So what we actually propose in the developments of our setups, it's mostly based on the instrument side. For example, on the pressure controllers, the valves, the sensors, flow sensors, CO2 sensors, pH control, feedback loop of the system, or parallelization of the system, miniaturization. So we're really on the setup itself, and the flow cells are then being developed by people with the respective expertise.
Okay, thank you.
Yeah.
All right. Any other question? Or we have to thank Krista again, right?
Thank you.
Right, so last but not least, we try again, Enrique. Hopefully, presentation is running now.
Coming. ¿Sí? Este sí que te lo ha reconocido. Perfecto. La pantalla completa. Y ya está. Okay. Okay, finally. Okay, thank you, Tomás. Thank you, everyone, to stay till this time. So, sorry for being just the one before the aperitif and the lunch. So, you will have to suffer the last presentation. Okay, let me talk about our company. Just a company created in 2011 with the concept of solving issues related to waste management in our country, in Spain. We started just with gasification, thinking on waste to energy. It was at the very beginning. It's been changing over the time, just because external factors, mainly, not because the technology. So our value proposition is related to three main pillars, which is waste recovery and circular economy, low carbon economy, and economical benefits. So at the end is a combination of science, technology, and economics. Okay, so we try to respond to different challenges. The point is, okay, now everyone is talking about zero waste, about circular economy, but we had to suffer from in 2011 and later on some changes in regulation that changed completely the business panorama. So just with science and technology wasn't enough to develop the business, and it is true that in the last years we've had a more clear and favorable panorama. To a point that we changed even the name of the company. It was Green Waste to Energy, and now it's a Green Enterprise, because now we are more focused on material valorization. So the environment we have, and this is important to explain, maybe for Tomás and some of the comments on the economics of the processes and so on, because sometimes you can't control the economics of your process, so the solution comes from outside. You mentioned about CO2, but we have an interesting situation now with, for example, just prices of waste managing changing, increasing a lot. So this makes that a process can be profitable in one region and non-profitable in another region. So depending on how much you pay for waste managing. So the barrier sometimes is just 25 euros, no more than this, multiplied by thousands of tons, and the feasibility comes not from the technology but from the economic side. So this is a reality we are suffering every day. So same project, same feedstock, same technology. In Alicante is feasible, and in, I don't know, in the north it's not feasible. So this is something to consider all the time. The same technology and so on. It is true that the situation with legislation, that the regulations is also helping in the deployment of any new processes. In particular, the landfill taxes and the new landfill regulations. I think you probably know, or at least you should know, I think, in 2030, less than 10% of waste will not go to landfill. So this is a huge opportunity, and we have raw material, which is just any type of waste, municipal solid waste, industrial solid waste, is an opportunity to be used as feedstock of any of the processes. Okay, what do? We just mixing gas. Okay, so our process is just pyrolysis gasification. Pyrolysis gasification, and from syngas we have projects in different areas. So we are now, for example, just very focused on pyrolysis oils from any type of feedstock. Also on thermal energy generation, on electricity generation as well. The last year has been a nightmare, so everyone asking for renewable gas and all the issue of gas. Hydrogen, Fischer-Tropsch synthesis, and methanation. So the point is, which are your boundary conditions in order to deploy your current project? So we've been focusing our main efforts in being flexible. So in thinking of this concept of reconfigurable biorefinery or something like this, okay, in order to deliver one or another product under the same facility and with the same concept. Which is our solution, our process. Our feedstock is always industrial solid waste or municipal solid waste, any type, even from the paper industry, paper mill, from whatever the industry is, just 28% carbon content. This is more or less the threshold. So there's a pretreatment and a gasification. The pretreatment is relevant. It's an added cost, not to be just neglected, but again, the changes in regulations are forcing everyone to circular economy. So it means that energy valorization is just at the top down of the waste hierarchy. So it means that we should try to avoid energy valorization and go for material valorization, which is our current main line of work. So a typical plant is just pretreatment and classification. The composting part goes in a different line. And what we get is just a small fraction of ashes. It depends on the feedstock that could go to landfill, and the syngas. And then from the syngas, the different products. I will go very quick to some examples. Okay. Also relevant to mention why we consider that this option on the type of pyrolysis we do offers some advantages over other systems available in the market. So we do not operate in just one reactor. It is not a fluidized bed or downdraft. So we just split the process in 3 different reactors. So a pyrolysis, a gasification, and a cracking chamber, just to avoid tars. This permits easier control, better control, and what is more important, to work with heterogeneous feedstock. Okay, so if I change my feedstock, I do not need to redesign any parts of the plant, just change operating conditions. And it is a tar-free process, which is a relevant result. Okay, just okay. We do not sell technology, so we just invest in the plants. So just we identify the feedstock, and we try to reach a deal with the owner of the feedstock, of the waste, and we invest in the plants. So we do not sell the plants. It is not a turnkey operation, so it's just an equity operation in any sector. Paper, food, agro-food industry, waste managers, meat, or whatever. Some examples of processes that we are now working on. Hydrogen. Everyone now is crazy about hydrogen. Okay, the point is, there's the feedstock, which is the waste, and through pyrolysis gasification, also with the help of a SOEC electrolyzer, as we play always with thermal energy, we have excess of thermal energy. Okay, there's the option of using a high temperature electrolyzer in order to just add some more hydrogen to our process. And then through a palladium membrane separation, just to get the hydrogen with the help of, it is separation and water gas shift in the same reactor, okay? And then for the production of hydrogen. How the numbers, how the final result on the profit of the process, how it comes to a profitable operation? Just because we are paid for the waste. So it is not just the operation on how feasible or the CO2 bonds or any parts of the CAPEX and the OPEX and so on. So it is also about having an income coming from the waste. Which type of waste? Any type. When this morning, I think was Joanna from CEPSA, talking about just how complex is a mix of waste just in the market. It looks like something like this. So it means that you find almost everything there. And the composition, again, almost everything. Non-metals, not organic fraction always. So this apparently is a disadvantage, but offers some advantages. Okay. Well, when we talk about feedstock, we talk about complex waste blends. Okay. For example, another of the projects is with the textile and footwear waste. Okay. So every things that you normally thrown away to your littering and so on. Okay, just playing with separation processes and then a mix of techniques. So this is one of the recent projects where we are now, this is a project under construction. There's solvolysis, there's pyrolysis, and there's HTL. Why this combination? So just in general, everything that works well with pyrolysis does not work well with HTL, and the opposite. High water content, okay, HTL welcome. Lower water content, pyrolysis, traditional pyrolysis comes as a solution. So a combination of the two technologies and playing with the different technologies is a good solution for a, I wouldn't say a biorefinery, but just a complex or hybrid refinery. Or also the possibility of reconfiguring or combining different processes. Depending on what? Depending on how much you are paid for the final product. Okay. This is another project we are conducting with several partners where the final products are hydrocracked pyrolysis oils and also methane, but coming from fermentation. So CO plus hydrogen, relation to 1, and in this case, just a biological process, so methanogenic microorganisms just working for us. The point with this approach is that we use almost all the heat, all the thermal energy available in the project. So we only have the pyrolysis, which is endothermic. The rest of the processes are exothermic. We have the support of a SOEC electrolyzer that can work in different modes as an electrolyzer, but also as oxy-combustion. So it depends on the final products. And we have hydrogen in the process as a vector to be used. It can be a final product or can be just an auxiliary product for the hydrocracking of the pyrolysis oils. Which is the, if you want, the driving element on the process? The price of the final product is so easy. Another example on HTL. This is not in our facility. This is in Denmark with people we are working with. I think it's the first plant on continuous HTL, okay, which is the interesting element, not just our colleague Patrick. And well, it seems under the under the energy consumption of the process, the thermodynamics of the process is really favorable. The key element is just an oscillating pump, so it's just changing your pressure from one place to another. So you recover almost all the energy, not all the energy, but most of the energy in the process. It is a very we think a promising project for sewage sludge, or even for textile. For textile, for example, it is just mixing with water. So it is the alternative in this case, where okay, at the end, what we obtain a mix of oils that go to a traditional refinery. This concept that Thomas mentioned of a hybrid biorefinery in a traditional refinery, it is the solution in most of the cases. So it's about retrofitting of already existing facilities. So we don't need to design and to construct new processes in order to make profit on all these flows of waste. Okay, these were just a few examples of some of the projects we are running. We are now in the process of setting up and building with the permits and so on, the first 5 plants here in Spain. Well, we will be happy of welcoming everyone in our facilities in Alicante. Okay, thank you very much.
Thank you, Enrique. I must say, I visit the facilities, they are really impressive. So you guys are doing a good job over there. So thank you for coming along today, and we open the forum for discussions. Any questions? Or everyone is hungry? I don't know. Jose, I'm sure you have a question. We've been talking about.
Yes, I was talking. It's readability, the technology, but I was thinking about the different lines do you have. So you receive the waste all mixed. I imagine that the problem is the separation.
No.
No?
Well. No, it depends on the type of waste. So a typical operation at the end, okay, we're a company, okay, so we look for the profitability of the operation. So this is so clear. So the first point is where the waste is. Second is how much is available. So this means that you need at least 40,000 tons. Below this quantity, just forget about an operation. Then is the quality of the feedstock. But the quality of the feedstock, and also which is your market for the products. We already have set up just contracts with oil companies for the pyrolysis oils and for the different products. But we are a zero waste company, so it means that at the end there's the pyrolysis oil, but if there's water coming from the biomass, okay, this is not good for the biofuels, but then you get an organic fraction, and in the organic fraction we deploy other processes in order to separate benzoic acid, acetic acid, polyphenols, caprolactam. So the point is conversion. And at the end, maybe as chemical engineers, we may think that you should fight for high conversion and high yield. But at the end, when you talk with the finance guy, he's talking about euros. And so it depends on the cost of pre-processing. So when pre-processing of the waste is an issue, or transport, so at the end it's about these very easy things. Then maybe a conversion of 45% is okay, more than enough for you. So you may get 70, okay, try, but at which cost? So it depends, and 45 is okay. So that's the point on the mixed blend of waste. One of the advantages we have with our reactor, with our pyrolysis reactor, is similar to a clinker reactor. Indirect heat, okay, from the fumes coming from the same process. So our plant is zero emission and works with own energy. So we only supply just energy at the very beginning, on the starting up, on the ramp up. But in operation, it takes the energy from part of the plastic. So we always run the mass and energy balance in order to make a self-sustainable plant, which means maybe 10-15%, no more than this, of the energy generated. And with this type of reactor, we control very well this heterogeneity. This means that we have plastics with different melting points, there's biomass, or almost everything. But again, it's a matter of residence time and just conversion.
Okay, thank you.
Right, any other question in the room? Otherwise, we will thank Enrique again and conclude the talks. Right, guys, so we have in the afternoon the poster session. Now we're gonna go for lunch. We have maybe, Jose wanted maybe to lead a lab tour if you want. If someone want to have a look to the catalysis lab here, Jose is happy to give you a quick tour before we go to the bus. That's one option. Otherwise, we meet you in the hall, right, down there, and we'll go to the bus. So, yeah, good. Let's enjoy some lunch. Everyone is hungry, or you want to see the lab or whatever. I'm going to go to the hall to hold the bus. And follow,